Okay, so today we are going over general chemistry, right? So you can just go on the site, there's free review sheets here, and then you just click on miles down. Yeah, and then go to maximize viewer, and then this is a little bit too big for me, zoom out, and then find general chemistry, page 1. So we're following mile down, and we're going to do a full review. So let's start with chapter 1, atomic structure. So atomic structure is about, literally in the name, atoms, right? So atoms, so you want to be able to see the periodic table. So here's the periodic table. I'm gonna leave it here. And so these are all the elements on the periodic table, and our world is made up of all these different elements. So for example, common examples: H2O, water, hydrogen's over here, oxygen's over here, right? Our world is made up of lots of oxygen, lots of carbon. Some of you may have heard of, like, for example, carbon dioxide. So for any beginners learning, you have the element here, and A is the mass number is equal to protons plus neutrons. So every atom is made up of protons, neutrons, and it's not listed here, but also electrons, right? So your protons, for review, are positively charged. Your electrons are negatively charged, right? And your neutrons are, can you guess? They're neutral, right? So, well, that doesn't look that good, does it? Whoops. Are neutral, right? So those are what your atoms are made up of. Protons, electrons, and neutrons, right? So A resembles the mass number, which is when you add the sum of your protons plus neutrons. So let's make up a fake element here. So the fake element has 2 protons and 2 neutrons, right? So let's say it was 2 and 2, whoops. So its mass number would then be 4, because you're just adding them together, 2 and 2, right? So that's how you would just calculate it, right? But on the periodic table, your mass number, so the mass number of hydrogen is, the mass number of hydrogen is 1, and the mass number of nitrogen is 7, right? So what does that also tell you? It has 7 neutrons, as it does protons if it's neutral, if it's not charged at all, right? And this is different from what we call atomic mass or atomic weight, right? Because your atomic weight, or your weighted average of isotopes, so weighted average of all the different versions of the possible the element can be in, is the weighted average. So the weighted average of nitrogen is 14, and you'll see that on your periodic table. That's usually the bigger number, right? And your mass number should be able to always tell you the number of protons, right? Well, not always, because you're going to have your atomic number, right? And your atomic number is what you see at the top here, 7. And it's like, well, I don't get it, because what if you have an element that is, negatively charged, -1 charge, it has a -1 charge, then what happens? Well, what happens is that you gain you gain an electron, right? But the number of protons will never change. You can only gain the electron and it'll become negative. Or you can lose electrons and you'll become positive, right? So we're only ever gaining or losing those electrons, right? Number of protons we're not gaining or removing, or else that would totally change the element that we're dealing with. So if nitrogen lost, 2 of its protons, then it would become boron, right? And I'll change it completely. But if I have nitrogen that is negatively charged for some reason it's negatively charged, let's say -1, then that means it gained an electron. It does not mean it gained, it does not mean it lost a proton. Okay. So yeah, know what mass number is, how to calculate for it, know atomic number, know atomic weight, and how to find it on the periodic table. How to find these things on the periodic table, okay? And then scientific contributions. So there were people who tried to figure out what's happening for the atom, and these people are Rutherford. These are the researchers, Bohr, the scientists, or in other words, Heisenberg, to help understand atoms, right? Hund, and Pauli. Those are different names, right? And so the Rutherford model is about electrons surrounding the nucleus. So if we look at a picture of an atom picture, so hopefully everyone's seen an atom before, but you have your nucleus here with the neutrons inside. And so the Rutherford model is basically that for a model, because all our models of pictures of atoms are based off what these scientists found out, right? So Rutherford exactly looks like this, right? So you have your neutrons in the middle. So electrons surround the nucleus, and this nucleus is obviously, like I said, neutral, right? Bohr model describe orbits in more detail. So what about the detail? He described farther orbits have higher energy, and that when a photon is emitted, n goes down and n goes up. So n is referring to the quantum numbers, which we'll go over after, right? So we'll go over after the n and quantum numbers, but I'll show the Bohr model first. So here's the Bohr model, and as you can see, we also have orbits now. We have clearly defined orbits that the electrons are going around. So the electrons are not just randomly moving around. They're moving around in particular orbits, and that's what the Bohr model is. And then the farther orbits from the nucleus have higher energy. And a photon is what I would call a light particle, right? So let's say you absorb light. You're going to have an electron. What's happening to your electron when it absorbs light? So a photon gets excited, or an electron, sorry, gets excited, and it moves to a higher energy level when it absorbs heat, okay? And when it absorbs heat, then it gets into this excited state, and that excited state is actually temporary. And then when it loses that, a photon is emitted with energy. So the photon is emitted, and then the electron has lower energy now, right? So now that it has lower energy, it goes back to a lower energy state. And as you can see, it's n equals 1 in this diagram. N equals 1 in this diagram. N is just a quantum number. It's also, you can think of it, n equals 1 as the first orbital. So it would be the lowest energy orbital, right? And the ground state is lower than excited state. So you should know ground versus excited state of an atom, which here. So an excited state of an atom is going to be in this further orbital, right? And the grounded state is going to be in its normal lower energy. So things in nature, as you can guess by what I just said, that things like to be, or not all things, but the electrons at least, they like to be in their grounded state. They'll be excited temporarily, but then go back. All right, you can read more about it another time, and about how photons, how it changes electrons and changes their position. All right, so now we're going to go into Heisenberg uncertainty. It is impossible to know the momentum and position of an electron simultaneously. So it is impossible to know the momentum and position simultaneously. This is referring to an electron's position and a momentum, okay? Yeah, that's all you have to know about it, really. Yeah, and so everything I said, by the way, about protons and the excited state and stuff and grounded state is in this ahead mnemonic. So absorbed light will lead to higher potential. You'll have an excited state, that's what I said, and you will have a distance from the nucleus. As we said, the further the orbital is, the higher the energy. When it's in ground state, it's closer to the nucleus, the electron, okay? So the Heisenberg uncertainty principle is also about the electrons. Hund's rule, electron only double up in orbital if all orbitals have one electron. All right, so let's go over Hund's rule. All right, so to keep it a little bit simple for everyone to understand, let's look at, I should have looked at Aufbau first, but let's look at here, Hund's rule. So in Hund's rule, you basically have orbitals, subshells, right? So you have shells and then you have subshells. So each box, 1s, and then 2s, sorry, and 2p. It's important to know electron configuration, but for now, I'll just simplify it. So for now, I'll just draw it out. So let's say this is your atom as we know of so far, with a nucleus. That's the nucleus, and then it has its other orbitals, right? So the thing is that the orbitals have subshells. So I can't draw it really well here, but subshells, atom, right? So the subshells look more complicated, but we don't have to complicate it right now. Just know that within a shell, or also known as the orbital, right? Or the n equals number, the n number, there's subshells, okay? And so in Hund's rule, we're depicting the subshells. So here there are 3 subshells. 1s is a subshell, 2s is a subshell, and 2p is a subshell. Okay, it'll make more sense later once you understand electron configuration. And if you want, you can skip to electron configuration first and learn that first, actually. But let's say you have this subshell 1s, or you're supposed to draw it like this, like a square. 2s, and then 2p has 3 of these. So it's based off, the number of these boxes is based off of SPDF, which we'll learn later is the quantum number. Should have learned the quantum numbers first. as well. But the Hund's rule is basically saying you need to fill up the boxes so that all the orbitals first have 1 electron. So you need to fill it up. Like here, this is not good because they don't have 1 electron. This is good because you have to fill them all up before you pair them. It's what it's saying. So I'll give an example of Hund's rule here. This one is a good one. So here we have 1, 2, 3, 4, 5, 6, 7 electrons. The arrows represent the electrons, and arrows going up are electrons that have a positive spin, and arrows going down are electrons with a negative spin. And you'll learn that with quantum numbers, so don't worry too much now. So you have 7, and then 1, 2, 3, 4, 5, 6. This one doesn't have 7. So here's a better picture. 1, 2, 3, 4, 5, 6, 7. So you have 7 here. And before you shouldn't be able to do this because this electron should be here. So what it's saying is that you need to have at least one of the electrons in the box first before you start pairing them. So 1, 2, 3, 4, 5, 6, 7. So I'm going to draw this one out. 1, 2, 3, 4, 5. So I have 7 electrons. So this is how you would draw your 7 electrons. You go 1, 2, 3, 4, positive spin first, 5, and then you would do your negative, 6, 7. And if I compare that to the image, it should be correct. So 1, 2, 3, 4, 5, 6, 7, up, down, up, down, up, up, up. Now this one should be the same, up, down, up, down, up, up, up. Okay, so that's the correct way of filling up and doing the orbital diagrams. This is called orbital diagrams. And we will learn more in a second. So I will remove that. I don't know how to remove this. There we go. Okay. Okay, so next thing is Pauli exclusion principle, which says that a paired electron must be positive half or negative half. Not or, but a pair should be positive and negative. So as we saw with Hund's rule, you can notice here that we don't just have, here we go, sorry, it's kind of slow. We don't just have we don't just have up, down, oops, what are we doing here? We don't just have up, down, we don't just have up, 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 up in each of the boxes. Because if that were the case, so I'm going to draw the boxes really quickly. If that were the case, then this would be correct, but it's not. It's wrong. Okay, this is wrong. Because it doesn't violate Hund's rule. It's actually fine for Hund's rule. Hund's rule is fine. It's fine. Technically, under Hund's rule alone, it's correct. But if you also follow Pauli exclusion principle, Pauli, right? You're gonna have this. If you're following Pauli exclusion principle, then guess what? This is not good because you need a down spin whenever it's paired with a positive spin. So what do you think was wrong with that? This was fine because it wasn't paired yet, so it's gonna be positive, right? By default. Okay, this was fine under Pauli principle, right? But this, when we draw the arrow, should go down. It should be the opposite. So whenever you pair them, you pair the 2 electrons in the suborbital, in the orbital, then it's up and then down. So positive half is the spin number, and then negative half. So that's what it means on the Pauli exclusion principle over here. Electrons must be paired positive half and negative half. Okay, so another recommendation I have is that before you learn the scientific contributions, it's probably best, especially Hund's rule and Pauli exclusion principle, to go over both your, so you need to go over both your quantum numbers, which we're actually going to go over right now, and you're going to also need to go how to draw orbital diagrams, and you want to go in depth with these two, okay? So now we're going to go over the quantum numbers. So quantum numbers is just a way, I like to think of it as a good analogy when I learned it, is just a way to find the address of where your electron is located. See, a lot of the theories are based around the electron, so special. So the quantum number is like finding the address of this electron and where it's located, right? So if it's like the address number of your electron. Okay, so if n is n is a quantum number, it's not an actual number here, but it holds possible values that are numbers. Okay, so quantum number n, there's L, there's ML, and there's MS. So n can equal, its name is also called the principal quantum number. L is also known as the azimuthal quantum number. ML is also known as the magnetic quantum number. MS is also known as the spin of the electron. So principal quantum number, or n, represents what energy level or subshell. So that's what we saw earlier on the excited versus ground state. So let's look at the Bohr model, excited versus ground state. So if you look at the Bohr model over here, we saw that the orbitals here, this is n equals 1, n equals 2, n equals 3. Okay, so we saw that the energy level or shell number. And on the periodic table, oh, this is useful here. On the periodic table, it's represented as 1, 2, 3, 4, 5. There's a lot of possible values, but it goes this way. So the principal quantum number is represented here from 1, 2, all these elements are 2, all of these elements are 3, 4, n equals 5 here, n equals 6 here, n equals 7. The only thing you'll notice though is with the transition metals in the middle here of the periodic table, notice how it goes, it actually starts from 3, the n equals 3 here, n equals 4 here, n equals 5 here, n equals 6. So just notice that. Those are different for n, or the principal quantum number in other words. So the possible values that the principal quantum number can be is any integer really, but like practically with the periodic table, it's like 1 through 7 here. There's some other notes, except for d/f orbitals, the shell number matches the row of the periodic table. So I think that's basically what I was saying earlier. The other one that looks funny is down here. So d and f orbitals, they actually just write it down for you here. So you can literally see d orbitals here, f is down here. So d and f are special. I already mentioned that d was special, but f is also special here. So with the principal quantum number, it's 4 and 5 here. So instead of being 4, it's 3 for transition metals here. The rest are 4 here. P and S are pretty following the pattern, right? All right. The next one is azimuthal or L. So L can equal any of these possible values. The way you memorize L is that it can be any number from 0 to n minus 1, a range. So let's say n is equal to 3. You need to know what L can equal based on what I just told you here. L can equal a range from 0 to n minus 1. So if n, whoops, it's not showing up very well here, n minus 1. So if n was equal to 3, then n minus 1, so 3 minus 1 is equal to 2. So that means my L can be a range from 0 to 2. So that means the possible values can be 0, 1, and 2. Those are the range of possible values that L can be based on my n value. Okay, and then you need to know that azimuthal, there are different, okay, I didn't know there was a g orbital as well. I've never seen that before. But yeah, 0, if L is equal to 0, then it's representing the s orbital, so you'll see it on the periodic table over here. This is where the s orbital lies. And then if you see P is there, and that would be here on the periodic table. D is over here, transition metals, and this one all in green, everything in green, right? And then everything F, this is L equals 3. I hope G is not common, but just memorize that when L is equal to 4, it's the G orbital. I would say these 4 are the most high yield because they're on the periodic table. And then magnetic, it's representing your orbital subtype. So integers from negative L to L. So basically, you can know your ML based on your L, right? So you need to memorize that ML is equal to a range of negative L to L. What does that mean? It means that if L, for example, was equal to 1, then ML is equal to negative 1, a range from negative 1 to 1, right? So you'd have negative 1, 0, and 1 as the possible values, okay? And a lot of practice questions. If you need help finding practice questions, we have them here. I'll show you them after we're done this chapter's review. And then electron spin. We already talked about electron spin, and electrons can spin in a positive direction or negative one. And so when ms can either only equal positive half or negative half, but it can be possible with any combination of quantum number. Ms could be positive or negative, right? It's not dependent on the other ones. Like these other ones, N, L, and M are dependent on each other. Or at least you can use formulas to find how they are related to each other. Okay. You can think of MS could kind of be whatever it wants to be. It can be positive or negative. It didn't matter whether L was 2 or 3 or 4. It just wants to be what it wants to be, right? That's MS. It's the easiest one. Haha. All right, anyway. Maximum electron in terms of N, and then you have maximum electrons in terms of the subshell. So here are your 3D shapes of the subshell and orbitals. It's actually down here, the picture. And so you have S orbital, which looks like a sphere. You have P orbital, which looks like a pair of dumbbells on the x-axis. And then D orbital is like 2 pairs of the dumbbells. and F orbital just looks maxed out with dumbbells. So it looks like it has axes on X, Y, and Z. So if you ever played Minecraft, you would know what X, Y, and Z was. But if you don't know, then X axis is moving left and right, Y axis is moving up and down, and then your Z axis is kind of moving toward and away from you. So it's like 3D kind of thing, okay? So those are different axes, right? And in these areas, the electrons, these are where the electrons would be, right? Because again, the quantum number, remember, of a specific electron. So let's say this electron had a quantum number of n equals 2, L equals 1, ML equals -1, and its spin is ms equals +1/2. So in combination of all of these quantum numbers together, that should give you the location of your electron. So again, what I said earlier, quantum numbers are like, it's like the address of the electron. Okay, and then for maximum electron in terms of this, so for these formulas, 2n squared, when would I use this formula? I would use this formula when I want to find how much maximum electrons that a shell, an energy shell, can have, right? So energy shell 2, how many electrons can that have? 2, it's 2 times 2 squared, right? So that's 2 times 4 is equal to 8. So an energy level of 2, which is over here, would be able to max hold, what do we get, 8 electrons, doing the math, right? So you have to do lots of practice questions to help you memorize the formulas. Flashcards can help, as well as you can also use the study tape here to help out. So you just go click on study tape, block it out, and see if you can remember it and recall that. And then for this formula, you would use this when you know the azimuthal number, so L. So if you are given L, then you can substitute L into here. So let's say L equals 1. So then you can substitute 4L. L is equal to 1 plus 2. 4 plus 2 is just 6, right? So that gives you 6. So there can be, what it tells you is that there can be a maximum of 6 electrons in the subshell L equals 1, which is the p orbital, right? So it's very highly problem-based to do chem. So what I advise is to do a lot of practice questions. It'll get you thinking a lot more and challenge you in ways you couldn't have imagined, right? Lastly, on this sheet, we're going to go over the Aufbau principle. So the Aufbau principle is basically that you have, so remember I said the orbital diagrams are based off of, I know we still have that, are based off, yes we do, are based off of the subshells, right? So we have the subshell that's filling up first. So this is, Aufbau kind of gives you the order in which the subshells get filled. So first we go 1s, then we go 2s, then we go 2p, then 3s, 3p, then 4s, 3d, and it goes diagonally like this. And this chart is basically just to help you memorize what is filling up first, right? So it's not necessarily, it's 1s, then it's 2s, but it's not then 3s, it's then 2p, and then it's 3s that gets filled. And what this will help you with is when you learn about electron configuration, which I'm surprised is not even mentioned on here at all. But to make you practice all of these principles in practice, you can go practice as well electron configuration. So for electron configuration, you need to know how to find, based on electron configuration, you need to be able to have an example question that asks you what an element is and what's its electron configuration. So it'll pull out any of these elements on the periodic table, ask you what's the electron configuration, and you would then you don't necessarily have to follow Aufbau, but basically the steps do follow this principle, right? You can use kind of like hacks to help you get through it. Okay, some other stuff you need to know is light energy. So this is just a formula. Energy equals Planck's constant times the speed of light. So the speed of light is just a constant, so you have to memorize that. Planck's is also a constant, so you just memorize 6.6 times 10 to the -34. And then Avogadro's number is very important. It represents 1 mole. So in chemistry, 1 mole is like saying, so let's say I have a dozen of eggs. That means I have 12 eggs. A dozen means 12. A mole means this number here. It's a very large number. So a mole is just to represent one large number, and that number is 6 times 10 to the -23, and you have to memorize these constants. And then that will help you with practice questions on light energy. So energy equals HF, and F is also equal to C over lambda, frequency. So frequency is also equal to C over lambda, and this is able to derive this equation that you see here. So E is equal to HC over lambda. That's how you get this larger equation from E equals HF. It's because when you F is equal to C lambda. So if you incorporate that into here, it becomes HC over lambda, right? And then lastly, we have diamagnetic versus paramagnetic. So if you have diamagnetic, see, this is representing your orbital, right? Diamagnetic is when you have that electron going up and then down, right? All electrons are paired now. But if I had, suddenly I had another orbital and one of them, the subshells, sorry, didn't have this pairing anymore, then we would get something that would be paramagnetic all of a sudden. So you have like something like paramagnetic, like that, two of them. So I think a paramagnetic, when you see a problem, is like parallel. They're going parallel. Diamagnetic is up and down, right? So parallel means unpaired, right? So there's not two electrons in one box, right? Diamagnetic, there's a pair. So paired and repels magnetic field. This one pulls a magnetic field, and you can have one or more unpaired. Keyword is unpaired and paired. Okay. Follows Hund's rules to build atoms' electron configuration. If one or more orbitals have just a single electron, atom is paramagnetic. If there are no unpaired electrons, then the atom is dimagnetic. Okay. Now I strongly advise to go and do practice questions now, because then it would be much easier to understand electron configuration, which is not even mentioned in the review sheet, which I find interesting, which is not good if you're a new learner either. So yeah, click on your first unit of general chemistry and just start your practice. The numbers follow the review sheet. So I will generate one just to show. Whoa, this is a long, what happened here? Alright guys, so as you can see, there's a little bit of an error happening here, which sucks. But basically what you want is practice questions. Alright, so the practice question successfully generated. The first time I generated it, what happened was it created an error. So I just clicked 5 questions and then there was no more error. It must have been because the server was running down. So if you ever get a question set and there's errors, it's because yeah, it's just generating, the server is a little bit down. So as you can see, you get your practice questions here nicely. You can strike through what you don't think is correct, and you can choose the correct answer based on what you think is correct. You can also screenshot so that you can copy and paste onto your copy the entire thing and paste it onto a review board that you need. So I pasted it, and now I can, let's say I have my digital notes or something, because I know a lot of people are using it. You can just paste it, and then you can write your notes on how you did the question, what you did wrong, and stuff like that. So it's easy, nice, easy screenshot tool there. The screenshot tool is up here as well, and the periodic table is here, so you can use that easily, no problem. You can also highlight text that you need and stuff like that. And yeah, that's it. And it generates nice free ones, so I'll give all of these for free. Just pause the video whenever. As you can see, those are the quantum numbers we were talking about, and ground state we were talking about, right? So these are all high yield. Paramagnetic we were talking about. Unpaired electrons we were talking about. All this stuff we were talking about. It's just testing you. Yeah, excited state to a lower energy state, and it's giving you the constants in order to find, and now you have to use the light formulas that we saw earlier. Okay, so that's it, and enjoy. Yeah. All right, so now we're on General Chemistry 2, Chapter 2 or Unit 2. This is about the periodic table trends, and this is the light mode. We're working on making the light mode better. Right now the dark mode is actually easier to see, but we'll do a light mode for now just for fun, I guess. So on the far first, so we have to first know how to name what periods and what groups are on the periodic table. So okay, so firstly I wanted to go over what were periods and groups on the periodic table, just because it's important to know, because you need to know what the periods would tell you and what the groups would tell you. So let's say you have hydrogen, right? So it's on the first period, which is, you can think of it from left to right or right to left horizontally, or side to side. You know, something, this is a better picture for people learning. So periods go from this way to this way, right? Or it could be vice versa, like that on this plane. And then groups are going downwards. So group 1 is this one, I'm gonna probably draw it on so people could see. So we're on classic paint tool. So your groups are going this way, right? So this is group 1, this is group 2, and then group 3 is over here actually, okay? And then 4. Notice how the transition metals are always a bit different, and also this F block over here, they're always kind of different than the rest when you're counting things, okay? So 5 and 6 and 7 and so on, right? And now the periods are going the other way, so I'm going to use there's no highlighter tool. I'm just gonna use the block here. So periods go from this way. So period 1 is here, 2 is here, and actually you count it like this. So where is it? You count it like this. This is actually a good table here for people to reference. So periods go from 1, 2, 3, 4, 5, 6, 7. And like we just reviewed before, periods tell you the principal quantum number n. Remember that. So the quantum number n, or also known as principal quantum number. So it's the principal quantum number n. Okay. So I hope that makes sense there. Let me go back. Sorry. So now that we understand, because this periodic table doesn't show you, which kind of sucks, but you should know that periods and groups. So here are the groups may also be called families, and as we will see soon, why that is. Oops, I can't really see well in light mode. So yeah, the families are going from, again, vertically top down. And so the first family we have here are alkali metals, or group 1, group 1 over here, right? They're all here. So who's in group 1? Hydrogen, lithium, sodium, potassium, rubidium, etc., right? So then that's group 1. And then you have family number 2, or group 2, right? Then you have your alkaline earth metals, and that would be beryllium, magnesium, calcium, etc., everything down this row. Transition metals, I've said before what they are. They're right here. And the interesting about transition metals is that they function not very different, but they function a little bit different than the other ones, as you notice just by their patterning, right? These rare earth metals in this F block. So transition metals, again, are in the D block, and then here's your F block, right? So this is D, and this is F down here, right? And so basically, these are actually inserted here. So you can think of them as in here. They're placed in here, but they ran out of space, so they put it like at the bottom over here, right? So they put it at the bottom or something. So these are kind of basically transition metals, right? But they're not, because they're called rare earth metal rows. So they are a bit different, and they have an F block. And then you have your post-transition metals over here. I don't believe those are too high yield to know, but you should know kind of what they are, right? And then here, you should know what the metalloids are, okay? And then you should know where your non-metals are. Whoops, metalloids and your non-metals. I actually don't like this diagram that shows non-metals. Let me show you different diagrams for metalloids, non-metals, and metals, so that it makes more sense later on. So we're going to move on now to halogens, which is group 6. Fluorine, chlorine, bromine, iodine, and these two at the bottom as well. So usually they're going to give you common elements like these that are showing up right here on the page. Noble gases are very, very important. So that includes helium, neon, argon, krypton, xenon, etc. And the reason why they're so important is, as we'll learn later, is the octet rule when we go into chapter 3 about bonding. I believe it's in that chapter. But next thing you should know that is not written on this chart is actually, which I'm surprised it's not written, is actually you need to know, and I'll write it down over here, you need to know general properties of metals, non-metals, metalloids, okay? And you need to know general properties of the families that we just talked about. So we'll go over those right now. Okay, so this should have been the first picture I should have showed everyone, which is a picture of metals versus non-metals versus metalloids. So we can separate these into their physical properties. So as you can see, the metals are all here on the left, and the right are non-metals, and then your metalloids are kind of making this staircase-like pattern, right? And you should know which elements belong to where. Hydrogen, oh, this is a more high-def picture here. This one is nice. You can use this one too. Okay, this one is good. You can use this one. There's other good ones on Google. So yeah. Now another thing is that we need to know the properties, right? So this is Professor Iman's notes that she's been kind to give for free to others online. So we're going to be going over some of her notes on metals, nonmetals, and metalloids. So good conductors are metals. They're malleable, ductile, lustrous, and they tend to lose electrons and become positively charged cations, meaning, so these two go hand in hand, right? So if you lose an electron, you're becoming more positive. And if you're becoming more positive, if you are positive, you are known as a cation. So you're a positively charged ion. And just food for like just as an additional fact, if you're not a cation and you're negatively charged, you're actually an anion. But this is not relevant right now. Anions are not relevant. The next thing is that nonmetals are not conductive, so you can think of them as having the opposite properties. They're not malleable or ductile, they're not lustrous, and they tend to gain electrons. They're gaining instead of losing this time. So if you're gaining E, you're gonna become what? More negatively charged. You're gonna become negatively charged. If you are negatively charged, then you're known as an anion. Okay, so those are our metals and nonmetals. So you can see how they're very contrasting and they're basically opposing each other. So if you just remember basically one of them, that metals are good conductors, malleable, ductile, lustrous, and that they tend to lose electrons and become positively charged cations, then memorizing nonmetals will be easier because it's basically the opposite. And then for metalloids, the way I remember them is that they just share characteristics of both metals and nonmetals. So they're just in between. And I hope that makes sense because on the periodic table, you could visually see that they're also in between metals and nonmetals. So it should make sense that their physical properties also match that depiction on the periodic table. All right, so let's see what's next here. So when you do the practice questions, this is the periodic table that appears for practice questions. And you can also sort them by their families. And you can use this interactive periodic table in order to help you memorize and understand which is where. Having it interactive is really nice. You can also click these buttons really quickly and understand, oh, I want to know what the halogens are. Boom. Noble gases, all in purple. It's nicely color-coded for you. And if you're ever doing a practice question where you don't know, because these are all just the symbols, if you wanted to find, let's say, a specific name, so iron, like let's say you didn't know a symbol for iron, and you unselect the filter, by the way, so iron shows up, right? Fe. And if you didn't know the symbols for copper, it's actually Cu, not Co, right? So if you're still learning, this interactive table is good, and you can just find it on, once you generate a practice questions, you can find on this top right corner here for your practice and just use that to learn more of the periodic table. And now we're going to go into the periodic table trends. So we have them at the like a second tab on there. You can learn it from there, or you can learn it from the mile down directly. See if I can get this up now. Okay, so to learn it from miles down directly, so we went over these and these, but we didn't necessarily go over their properties quite yet. But we'll go over the trends before we go over these properties, because these properties are mostly memory based, memorizing the families and how they work. So the main thing about periodic trends, or the periodic table trends, is that you have this ZF, and it looks funny. It's So here's a good picture of effective nuclear charge, also known as ZF, right? So Z, effective nuclear charge, is equal to Z minus S. So this is a good picture where Z is depicting the atomic number. You won't be able to see that here. You can know the atomic number by the periodic table if you know the element's atomic number. So you can find the atomic numbers on the periodic table. And then this ZF formula is important to memorize as well, and to be able to calculate for effective nuclear charge. So you would have to do practice questions to get used to how to do that. And then S is equal to the shielding constant. So the shielding constant is the number of, here, this is another good picture, is the number of the, wait, this looks weird. So basically what you have to know for S is that it's the core electrons, it's not the valence electrons. So I'm going to quickly go over what's the difference between core and valence electrons, or inner or outer electrons, basically different wording for the same thing. So you have your nucleus, that's your nucleus, and then you have your orbitals, right? So this is your n equals number, remember? And then what happens is that you have your valence electrons on the outside, like this, right? So if I had, let's say I had 2 out on the outside, and then let's say I had a few like this on the inside, this one is filled up with like that actually can't be filled up that much over there. Okay, let's say it's just all filled up in some way. So the core electrons are the ones that are not on this outer shell, which is also known as valence electrons. So outer versus inner. So inner I'm just painting in blue for an example to show. This is just an example, right? And so another thing you need to be able to do is use the formula to find ZF, so your effective nuclear charge. So if we look back here, the formula is Z minus S. So there's a good example here by the AI where you are trying to figure out what the effective nuclear charge is of sodium. So what you do is first, okay, it already tells you identify the atomic number, but it doesn't tell you how. So basically how you identify it is you go on your periodic grid, or table, sorry, and you go to find sodium. Sodium's right here. And you look at the atomic number, it's 7. It's 11, sorry. It's 11, right? Z equals 11. So then what you do is now we need to find S. So we know Z, now we need to find S. So to find S, we need to know how many electrons are in the outer shell and how many were in the inner shell. I just reviewed the inner versus outer, right? So valence is outer and core in this terminology is inner. So the reason why they determine electron configuration first, and the other reason why I said that electron configuration since chapter 1 to find them is really important, and they didn't give any practice problems, so you need to practice how to find electron configuration. But for sodium, they already gave it to you here: 1s2, 2s2, 2p6, 3s1. If you don't know how to find the electron configuration of sodium or any of the elements on the periodic table, you gotta search up how to find electron configuration on it, right? And get used to doing many practice problems for that before you move on. And then you're going to use that electron configuration. So what it tells you here is that S2 means the orbital is filled with 2 electrons. S2 is filled, P6 is fully filled, and then S1 is halfway filled. Its full amount is 2. S can take a max of 2, I think. Right, so 3S1 is just telling you that you have 1 there, and the rest, 6, 7, 8, 9, 10, are your core shells. So the valence shell, to determine the valence shell, you need to look at the principal quantum number. You need to find which one is the highest. Remember, we were saying that if n is equal to 1, it's this one, right? If n is equal to 2, it's this one. If n is equal to 3, it's the most outer one. So now if you look at back here, at this electron configuration, oh, why does it look like that small? Okay, it didn't go well, but if you look at over here of electron configuration, you can see that 1s2 is filled. Okay, this is filled too much, by the way. This is just hypothetical example, but it's filled with 2 electrons. 2, and it's satisfied. Moves on. 2s2, filled, and then satisfied. This is 2. Okay, and then p6, 2p6 is also there, filled. We need to fill that. And then last one is 3, 3s1. So valence shell, again, was the highest principal quantum number. Okay, now we're going to find the shielding constant. Now the shielding constant just means what the core shells are. The core electrons are. So it was 10. You don't need to do, I don't know why I made this as a separate step. You don't need to do that. If you did this, that's good enough. If you do this, that's also fine. You can just use the highest principal quantum number to look at it and know right away, like, whatever's on the highest principal quantum number is on your valence shell. Those would be your valence electrons. And this exponent is not actually an exponent. It just shows a number of electrons. So if you add 6 plus 2 plus 2, that'll give you 10. So those are your core electrons, right? So you don't need to do this extra step, and you also don't necessarily need to do this. You can do this in your head. And then that you plug into your formula, 11 minus 10, and you get positive 1. Okay. So that's that one. And on the periodic table, you can use the periodic table to know the trend, meaning elements from the left side have low effective nuclear charge, and then those on the right side have higher effective nuclear charge. And then these diagrams also show you other trends for other things. So IE stands for ionization energy. So you need to know what ionization energy is. You need to know this trend that it moves up if you move upward on the table. So these elements that are going more up are going to be higher. Elements that are over here are going to be also higher in ionization energy. So it's going more like, kind of like a diagonal, right? And then effective affinity, or EA. So this one is electron affinity, and noble gases have no affinity for an electron. So that's why it's in white over here. That's why it says 8A. If you don't know what A elements are versus B elements are, you would need to know that as well. So A elements are main group representative filling S and P orbital, while group B elements are filling D and F. So again, A is in red in this diagram at least. and then B elements are in gray in this diagram. So when they say 8A, it just refers to the noble gases. So now gain electron, delta, so first ionization energies are important, as well as second ionization energies. Maybe not as much because it's not written on here, but it is important to know. And you'll see those come up in your practice problems. So definitely what practice problems will make you do. For example, in a practice problem, they'll give you different elements. So if I give you xenon and then, I don't know, helium, and then let's say I gave you copper, a practice question will typically give you 3 elements, and then you would have to rank them from lowest to highest or highest to lowest. You have to rank them in terms of whether they have high or low effective nuclear charge, whether they have high or low ionization energy or second ionization energy, whether or not they have high or low electron affinity. Do they have affinity for an electron? Noble gases couldn't care to have more because they are satisfied already by the octave rule, which we'll go over again. But that's in chapter 3. The atomic size. And then there's also electronegativity. Of the noble gases, only Kr and Xe have electronegativity. So these are common electronegativities to memorize. And for atomic size, it says that basically cations are smaller than neutral, and anions are the larger ones. That's what it's saying. So small to large this way. So I found this website. It's good to search up, like, this is not sponsored by me or anything, but basically whenever you do research, you can find what you're looking for. So I was at properties of metals for the MCAT, and I just found this resource that you could use here. And if you click element families, you can go through alkali metals. Whoa, it has highlighting for the site apparently, so you could do that. So read through what the key properties are for it. You don't necessarily have to know everything like that, but you have to have like a general idea of what would happen. Alkali earth metals, what would happen here, right? See, it even tells you the MCAT loves testing calcium magnesium in biological context. When you see these ions of passion, think alkaline earth metals. So it's even connecting ideas for you, right? Chalcogens, halogens. So pause and read these things, or just go on the site and find it. Have no fear of ice-cold beer is a good mnemonic to memorize your diatomic elements on the periodic table as well, which I'm surprised is not on the mile down review sheets. And then noble gases, and then there's a summary table. So the summary table will be good for a lot of people, so I'll just sit and wait here if you need to screenshot that. Okay, so now, let's see. So I did want to go over diatomic elements just because I didn't see it in the review sheets, which is not good. So diatomic elements are, like I said, have no fear of ice-cold beer. That stands for hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine. And they look very simple on the periodic table, so the ones in yellow are your diatomic molecules. So these elements can exist as diatomic molecules. And what it means to be a diatomic molecule is that it's a pair element that can naturally exist as molecules made of two identical bonded together. So that's why you could see H2 together, N2, F2, O2, I2, Cl2, Br2. So all of these elements can appear in kind of together in pairs, right? Pairs with itself, by the way. Okay, so the next chapter is 3 when we come back. Okay, so that's end of chapter 2. Okay, so now we're on General Chemistry 3, which is about bonding and chemical interactions. I will stay on light mode for now, and then we'll go from there. So bonding and chemical interactions is going to be about how these elements in the periodic table are able to interact with each other and eventually bond. Okay, so they can bond together, meaning they're kind of like connected, right? So if you ever look at a Lewis structure diagram, so you need to know what a Lewis structure diagram is. So you need to know how to draw, so search up on Google how to draw Lewis structure diagrams. Okay, so you need to know this. This is important to know how to do. So that will come from your practice questions, right? So do your practice questions for chapter 3. But before you do those, you should understand some of these basics that we're gonna go over right now. So first of all, let's start with this diagram over here because it's a good overview. So you can bond two elements together, right? And between those two elements, there's electronegativity difference, or there could be a lack thereof. There could be no difference. And if you have no difference in electronegativity, then you're non-polar covalent over here on this end. If that means the bond type, the type of bond that happens is called non-polar covalent, and we'll go over more in detail soon. If your electronegativity difference between the two elements is 0.5 to 1.7, so it's a range, right? 0.5 to 1.7, any number between those is polar covalent bond. It's a polar covalent bond. And then anything above 1.7, so 1.7 plus, is a ionic bond. Okay, so recall electronegativity can be found here, right? So this is just the general periodic trend rule, and it doesn't give you the exact given electronegativity. So I think pretty much the test provider should give you the given electronegativity. Let's look at this electronegativity difference calculation over here. So electronegativity difference is 1.6 minus 2. There could be a metal in the bond. So you know what? None of this is not good. Okay, so here's a good picture showing how to calculate electronegativity difference. So you're going to be given the electronegativity of, let's say, chlorine, and it says chlorine is 3.6. That's what the question tells you. And it says electronegativity difference, electronegativity of sodium is 0.93. So what you do to find the difference in the electronegativity is you minus the electronegativity minus the other electronegativity, right? And that will give you a number. And if that number is higher than 1.7, you have ionic. So in the case of NaCl, when the NaCl molecule forms, they are forming an ionic bond. And when you have an ionic bond, by the way, it will create a crystal lattice structure. I don't know why this is not on your review sheets, but ionic bond creates crystal lattice structure. So if you type this in Google, crystal. So notice how the structure is very rigid. Ionic bonds are very strong, right? So look at this crystal lattice structure here. It's very structured and very strong. And if you think of the opposite, right? If you're thinking of, like, let's say you're thinking of gas particles that are just complete opposite. They're floating everywhere. There's high entropy or like dispersion of these particles, right? So they have they're very okay. Let's. I think my brain's not working. Maybe I need to delete this. Should I delete this? Are you not deleting this? It's on the recording. Okay, so that's how you calculate your electronegativity. It's very simple. It's just subtraction, and based on the subtraction, you can know whether you have a non-polar covalent, polar covalent, or ionic bond. Remember that if it's above 1.7, it's ionic. If it's between the numbers of 1.5 to 1.7, then it's polar covalent, right? If it's 0 to 0.5, then it's non-polar covalent, and it's a range. Remember that. Now we're going to go into what is a covalent bond. So covalent bond can be contrasted with what is an ionic bond, okay? So you can either have a covalent bond or an ionic bond, right? So if you have a covalent bond, it means you have a formed bond via the sharing of electrons. The key word is sharing. They're sharing electrons. Ionic bonds are formed by the transfer of electrons, one or more electrons, right? So the key words here are covalent bond is sharing, and ionic bonds are transferring electrons. And you can read through more detail later on your own because it'll help you be more of an active learner too, right? So bond order for covalent bonds refers to whether a covalent bond is a single, double, or triple bond. As bond order increases, bond strength increases, bond energy increases, bond length decreases. So not only you don't just want to memorize this flat out. You want to understand, why does this occur? Why? Sorry, that doesn't look like a good why. But why does that occur? So I'll put a question mark here, right? Why? So let's go to sigma and pi bonds down here because that'll help explain bond order and why this occurs, right? So if I have a single bond, also known as one pi bond, right? A single bond looks like this. H and O here are single bonded, right? So if I have H and O single bonded, right? I can also have, let's say I have O and C in carbon dioxide double bonded like that. Double bond and a triple bond is represented as 3 lines instead of 2, right? So I hope that makes sense. Single bond is 1 line connecting the 2 elements. Double bond is 2 lines. Triple bond is 3 lines. Okay? And if you have a single bond, you have 1 sigma for the single bond. And then for the double bond, it's made up of 1 sigma and 1 pi. For the triple bond, it's made up of 2 pi, 1 sigma. So you can just memorize it flat out. You don't necessarily have to understand too much of why, but you need to know that pi on its own is actually strong. Sorry, I meant the sigma bond alone is actually strong, right? So I was referring, so sigma, I keep saying it wrong, but pi is the one that looks like this, and sigma is the one that looks like this, the circular one, right? So if you go here, sigma versus pi bond, sigma alone is stronger than a pi bond and forms every single basic covalent bond. And when you have a pi addition, so you add a pi, side to side overlap, and only exists alongside an existing single bond in double or triple bonds. So that's when we add the pi, right? And when sigma and pi are combined together, it makes for a very strong interaction. So while a double bond has 1 sigma plus 1 pi, is harder to break than a single bond, a sigma alone. The sigma bond itself provides the strongest and most foundational single interaction. So a pi alone is not stronger than a sigma bond alone. And also pi doesn't seem to appear alone. It appears with sigma. But when they're with each other, they're stronger than 1 pi alone. So a double bond, in other words, a double bond is going to be stronger than a single bond, and a triple bond is going to be stronger than a double bond, right? So I hope that makes sense. And also you can think of it visually, right? So let's say you have these H and O is only connected by 1 line, so it's pretty weak. C and O is connected by 2 lines, so it's medium weak or medium strong. It's in the middle. And then you can think of it visually if you're a visual learner, like X and X here. These are just example elements. X is just a placeholder. These 3 lines, they're connected with 3 lines. So they're connected with the thickest kind of rope looking, it looks like a rope. So you can think of it that way, that it's the strongest. But you also have to think about its composition of sigma and pi here and memorize how many, right? So then it says here, as your bond order increases, so as you go from single to triple bond, right, your bond strength increases. So we already just went through that. We did not go over bond energy and how it changes your bond length. So let's go over that. So if you have a strong bond, right, between 2 elements, if you're close, like let's say you're close with someone, right, you're going to have a strong bond. So the distance between these 2 elements is going to be not far. It's going to be close. So the length is going to decrease because they have a strong bond. They're really attracted to one another. So the elements are close together. So that's another way to think of why the bond length decreases. You also want to think about why does the bond energy increase if your bond order increases. So your bond energy increases because what happens, so you can think of energy increase because as you see here, bond energy increases because sharing more electron pairs creates a stronger electrostatic attraction between the positive nuclei and negative electron cloud. So basically what it's saying is that you have these positive nuclei and wait, what is this? None of these are good examples. Wow, I literally have to do so much to make this. So if you have more shared electrons, it creates a tighter, stronger attractive pull between the nuclei. Right, so it's going to increase in energy. Why does it increase in energy? The increase in bond energy happens because a higher bond order creates a deeper electrostatic potential energy as well. Okay, so we won't go over that right now because then you would have to understand other physics stuff. But to tie it to physics, you could tie it and learn it with physics as well. Chemistry goes really well with physics, so if you're learning chemistry, highly advised to learn it with physics. That's also why the exam is structured that way. You have your chemical physical section, right? And that's why they structured it, because the concepts are related to one another. But you don't have to worry about that now as a beginner student. You just need to learn these discrete kind of facts and then kind of make the connections as you master the material. And those connections will slowly but surely happen on their own. So we just went over these crystal lattice that I showed you. We already went over what a cation is, what an anion is, which is great. And then ionic bonds, we went over that, what they are. And then non-polar bonds, we went over what the electronegativity difference was, which is great. Coordinate covalent bonds we haven't went over. So what a coordinate covalent bond is this a special type of covalent bond. It's still a covalent bond, right? But the thing is that one atom provides both the bonding electrons, so both the shared electrons. And this is most found in Lewis acid-base chemistry. So Lewis acid-base chemistry is actually all the way in chapter, let's see, Lewis acid-base should be around 10-ish. Solutions, yeah, 10. It's exactly chapter 10. So acid and bases. And this is Lewis acid and base down here, which you'll learn later in chapter 10. But for now, you can kind of gloss over that, know it's relevant for that, and also know what it looks like. So here, covalent bond. So this is a good image that shows here that atom A is sharing both the electrons. So usually it would be a sharing of one and the other one shares as well, right? But this one, only one of them sharing both. Okay, so that's a coordinate covalent bond. Let's look at a nonpolar covalent bond examples. So here's your nonpolar covalent bond, right? So your nonpolar covalent bond, each of them share. There's an equal sharing, right? Now, and it looks like that, right? So one of this hydrogen is sharing with this hydrogen, right? Now quickly go over polar versus nonpolar. So polar, you see these plus and minus symbols everywhere, right? And that's because there's an electronegativity difference. That's why I call it polar. They're different. Like if someone said they're polar opposites, yeah, polar is like different, right? So these have a difference in electronegativity. So there's unequal sharing of electrons, but they're still sharing the electrons. It's just unequal. So we still call it covalent, but it's polar covalent. And the thing about this is that the positive, partially, this means partially positive, partially negative. It doesn't mean that it's fully positive or fully negative. You don't get cations or anions. You only get cations and anions in an ionic bond, okay? And then negative means this is the more electronegative atom. So it's going to want to have electrons. Now, another thing to be able to calculate is your formal charge. And that's why I mentioned at the very start of the section that you need to know how to draw Lewis structure diagrams, because to be able to do your formal charge calculations, you need to know how to draw those diagrams. So formal charge is equal to valence electrons. So we already went over what valence electrons are, right? Valence electrons, I kind of made it look confusing here. Valence electrons minus dots minus sticks. There's actually a different formula, but a lot of people like this formula because it's more simpler. So let's see it in action. Formal charge. Oh. It's way better to learn via the textbook. Alright. So this is another version of doing the formal charge. There's many different versions, but the easiest one is if you draw your Lewis dot structure, which is one of these, and then you're able to calculate for the formal charge. So you know what, this picture is already a very good example. So go over how to draw your Lewis structure diagram first, and then you're gonna learn how to calculate formal charge based on Lewis structure, because you'll need to know how many dots and sticks there are, right? And the only way to know that is if you drew the Lewis dot structure diagram. So here we could see from C to O, the bond between them, there's 2 sticks, right? And we can see from on O, there's 4 dots, 1, 2, 3, 4, right? This is another good picture here. So H's formal charge is different. By the way, each atom has a different formal charge here. So O is 0. So 6. So it's doing electrons, 6. So electrons you get from your periodic table, by the way, of what you would get normally. So oxygen is 6, because if you go periodic table, oops. Let's go to oxygen. 1, 2, 3, 4, 5, 6. This is how you find your valence electrons. You count 1, 2, 3, 4, 5, 6. Recall chapter 2 of how to do that. 7, 8 is when you get to your noble gases. All noble gases should have 8 valence electrons. If they don't, they should have a full shell, a valence shell anyway. So oxygen is 6. Whoops. So oxygen was 6 minus dots. So if you look at this picture, it has 4 dots minus the sticks, which is 2. So they swapped the formula a little bit. So it's 4 minus 2, but you should get the same answer, which is 0. 6 minus 4 minus 2 is 0. So the formal charge of the oxygen in this scenario is 0. It's not always 0. It has to depend on how these bonds has how many dots and sticks there are, right? So you need to be able to draw that. Okay, now we just finished doing your formal charge, right? We're going to go into intermolecular forces. So these are forces that occur naturally because of the bonds that happen. So if you have a hydrogen bond, that is bonded to FON, any H, so FON is a good mnemonic. So H bonded to F is a very strong electronegativity difference. H bonded to O is strong, and H bonded to N is also a strong electronegativity difference. So this would lead to, so notice the FON on over here is that these elements are all the way on the right, right? FON, fluorine, oxygen, nitrogen, and here's hydrogen all the way on the left. So as you can see, they're very different in electronegativity. Recall your chapter 2 periodic trends of electronegativity. So these are very high and hydrogen is very low. So they have very different electronegativities, right? So here's the trend. So hydrogen would be here and the FON would be over here, right? So this is related to this. And so that's why you get hydrogen bonds being so strong. They're so strong. Dipole means you have a dipole. No, what's a dipole? I already forgot. Okay, this is my last one. So dipole bond forces attractive intermolecular reaction between two polar molecules. It happens when the partial positive end of one molecule lines up next to it and pulls the partial negative end of the neighboring. So you have this polar bond, this neighboring, right? So the attraction is what we're looking for here. They're opposite partial attraction. So remember, this looks like your polar covalent, right? Okay, now that happened. They're intermolecular. They're not intramolecular. Intermolecular is different, right? This is, pretend this is a molecule. Here, this is intermolecular. So this is a whole molecule. This is a whole molecule. Intermolecular is between those two molecules. It's not between these two, right? There can be electronegativity between these two, but there can also be electronegativity between the molecules. And in that scenario, you get dipole-dipole, right? So remember, intermolecular, between the two molecules. Hydrogen, we went over hydrogen bonding, or hydrogen forces. Dipole-dipole, we went over. Hydrogen, by the way, is a special type of dipole-dipole. It's a strong type of dipole-dipole. And London dispersion is the weakest. It happens naturally. It's also known as van der Waals forces. It's a general term that includes dipole-dipole forces and London dispersion forces. So it includes both of them. So then we have our last but not least, VSEPR, or VSEPR. I call it VSEPR. And basically, VSEPR theory is just to predict the molecule shape. So how come water molecule is not a linear shape, but it's actually bent like this? How come CO2 is actually straight like this? How come we can't just draw H2O like in A? Well, we can, but how come it's not representative of its shape according to VSEPR? Well, according to VSEPR, H2O has 1, 2, 3, 4. 1, 2, 3, 4. Has a bent shape. What was I doing here? Now I'm just tired, man. Okay, so let's first go over electronic geometry. So electronic geometry is your bonded and lone pairs treated the same. So when you have bonded and lone pairs that are treated the same, it means that whatever electrons are bonded, so these lines represent bonded electrons, right? And then these lone pairs, or the dots, are the lone pairs, right? The non-bonded electrons. So that's your electronic geometry. So this is over here. You can also have molecular shape. So your VSEPR predicts for these two. It predicts for electronic geometry and it predicts for the molecular shape of the molecule. It's when the lone pairs take up less space than the bond to another atom. In other words, the lone pairs cause there to be less space because they're taking up space. So they cause there to be less space in that area because the lone pairs are taking up space. So, but electronic geometry is where it treats them the same. So it's taking up space in the same way. Okay, so hybridization is when your orbitals hybridize. Essentially, they're coming together, and this is referring to your quantum numbers. Remember your azimuthal quantum numbers, so those are exactly that. Yep, looks like electron configuration almost too. And then electron groups around the central atom. So let's count how many electron groups around the central atom of water is. So there is 1, 2. So, wait, what? Why does this diagram look so bad? Well, you're only counting the electron pairs around the central atom. So in this case, around the central atom for carbon, is only 4. And there's no lone pairs around the central atom. Remember, this has to be around the central atom. This is a key part over here. The electron groups around central atom. So although you see here, technically 1, 2, 3, 4, 5, 6, 7, 8, there's no such thing as 8 here. You can't count up to 8. There's only 6. So you have to count around the central atom. What is around it? Carbon itself has no lone pairs around it. It only has 1, 2, 3, 4 sticks, right? Bonded. So this is its 4 electron groups around it, right? And it would then be tetrahedral. But why is it not bent like water? Because water has a different molecular shape because it has 2 lone pairs. But carbon has 0. Right, so if we go back to water, as you can see, oxygen has the 2 lone pairs. Carbon has no lone pairs. The oxygens on the outside have them, but the carbon, being the central atom, has none. Okay, be careful when you're counting electron groups around the central atom. So you basically have to memorize and be able to predict based on the molecule you're given with the electrons, based on Lewis dot diagram, what is the electronic geometry and what would be the molecular geometry. So do lots of practice questions on those, figuring those two out. And this whole idea is based off of Vesper. Alright guys, so now we're on General Chemistry 4 about compounds and stoichiometry. So what you have to know in this situation is, this chapter will go by quickly for me to teach because it's mostly halfway memorization, and then there's some practice problems which you most of the time you gotta learn on your own, right? So first starts with naming ions, and then there's acid names, which will be relevant when you learn acid and bases in chapter, I think 10. Yeah, chapter 10, acids and bases. So for chapter 4, let's go back. Let's start with the naming because all you really have to do is start memorizing these things. So for elements, usually metals that can form more than one positive ion, the charge is indicated by a Roman numeral in parentheses following the name of the element. So what it means is that, so this is iron, Fe is iron, right? 2, it resembles its charge. So you're resembling its charge. Same with copper down here. So if it's 2 plus, you have the Roman numeral 2. So if you don't know your Roman numerals, you should know at least, I would say up to 1, 2, and 3. Roman numerals is just like tallies. They look like tallies until you hit 5. Actually, no, until you hit 4. But you likely not see more than 3. 4 looks like this. Oops. And 5 is just a V. So know your Roman numerals a little bit. And then the older method is using us and ik to name the atoms with a charge. So you won't see this as much, but you should know this. So remember that if it ends with us, then it's referring to the charge. Ik is referring to a greater charge. Us is referring to the charge, and ik is a greater charge, and it's known as the older method to this method up here using Roman numerals. Now, you could probably guess why people decided to switch the naming method. It's because this is a little bit more specific with the exact charge. Whereas this, you could just tell if it's less than or greater than in terms of charge, right? So monoatomic anions drop the ending of the name and add "ide." So hydride, "ide." So this is hydrogen, and they added "ide" instead of saying the full hydrogen. And so this is the suffix they're adding to all of these because these are monoatomic anions. So notice they are all negatively charged. You should already know, since by chapter 2, reviewing what anions and cations are, you should know that anions are all negatively charged. When people, I don't know, everybody is naming oxyanions, they're polyatomic anions that contain oxygen. So if you have more oxygen, you're going to get "ate" as a suffix, and if you have less oxygen, you're going to get "ite." So when someone says nitrate, it has O3, NO3, right? But when someone says nitrite, it's NO2. So if you use "ite," it's less oxygen. If you use "ate," it's more oxygen. And you kind of have to memorize that. In extended series of oxyanions, prefixes are also used. So prefixes are things that come before. Suffixes come after the root word. So here we have hypo, more oxygen, hypo, or they might use per instead. So hypo is here and per is over here. And hyper, they use hyper or per, right? So over here is perchlorate, and that means a lot of oxygen, more oxygen. Then you have less oxygen with hypo. So this only has 1 oxygen. This chlorite has 2. This chlorate has 3. So this is following the one we just learned above here. So all of this region is learning about how to name oxyanions, and then all of this region follows charges, and this region follows for only monatomic anions. And then for polyatomic anions, they gain H plus 2 for anions of lower charge add the word hydrogen or dihydrogen to the front. So you can see here they have hydrogen, so then you just add hydrogen. This one has 2 hydrogens, so you'll say dihydrogen. So this one here, dihydrogen phosphate, because they gain an H plus, and you'll learn later on why certain molecules might gain an H plus when you learn about things like acids and bases. For acid names, you usually have "ic" at the end, like hydrofluoric acid or something. you have more oxygen, have one more oxygen than us, and then us has one fewer oxygen than ick. So yeah, do some practice questions of learning to name acids, and once you get good at that, that means you passed. Just reviewing this alone doesn't make you good at it, right? Okay, so the next thing that I'm going through the easy stuff first and then the harder stuff last to explain. So we'll go over the types of reactions first, which is over here. Types of reactions, so you can have a combination reaction. You might also see this on Google, or any other textbooks might say it's also known as like a synthesis reaction. Basically, yeah, you are synthesizing two things, so A plus B will give you AB. So the general formula for combination isn't written there, but it looks like this, kind of. And then for decomposition, single reactant breaks down. Basically what happens is AB goes to A plus B. So that's your decomposition. So if you were given a chemical reaction like this, you should be able to successfully identify what type of reaction that you're looking at. Is it decomposition, or is it a combination? Or it could be any of these as well. So combustion involves a fuel, usually a hydrocarbon and O2, commonly forms CO2 and H2O. So this right here is the hydrocarbon, CH. And then here is the oxygen, the gas, oxygen gas, O2. Remember, oxygen is a diatomic molecule, and then it goes and turns into CO2, H2O. And with this formula, you'll know that this is a combustion reaction over here. Okay, so the next one to know is single displacement and double displacement. So we'll go over single displacement. So in single displacement, you get A and AB. So, A plus BC. So this is a general formula. So A plus BC, think of it as two of these are swapping their places in a single displacement. So basically A and B are swapping their places, so you get B plus AC, right? So you get CO, copper over here, with like here, so they're just swapping places. Ag is leaving to be by itself. All right, so in double displacement, it's also known as metathesis, where you basically get even more swapping of places. So you get the Ca, Cl, Ag, NO3, right? Ca combines with NO3, and AgCl combine together. So these two are coming together, and these two are coming together. So it's a double displacement. So they're swapping. So CO will be with NO3, and then Cl will be with Ag. All right. Neutralization reaction is just a type of double displacement, but it's for acid and bases, and usually acid and bases will combine to form salt plus H2O. This is the only one where they actually gave the general formula and also a specific example. So here is the general formula: acid plus base to salt plus H2O. If you don't know the general formulas, you can also just types of reactions. You can also just look at any of these images, and they can help you understand single displacement, double displacement, reactions, synthesis, and decomposition reactions. Okay, so now that that is over, the harder part of this chapter is actually understanding equivalence and normality, and compound formulas. So it's not hard to understand these formulas, but the harder part is doing the practice questions for them. So I'll probably show examples soon after I go through the definitions. So equivalence and normality. So equivalent mass is the mass of an acid that yields 1 mole of H+, or mass of a base that reacts with 1 mole of H+. So an equivalent is essentially how much, in terms of mass, which is usually in grams, that will give 1 mole of H+. Okay, and the gram equivalent weight is molar mass over the mole H+, or electron number. Equivalence is the mass of the compound over the gram equivalent weight. And then normality is the equivalence over the liter. So for acids, the number of equivalents, N, is the number of H+ available from the formula unit, right? So if we go back to find an, where is it? To find an acid, actually we'll do a practice question for that soon. Molarity is another one. So molarity is equal to normality over the mole H+, or E-. So we will go through practice questions for each of those. Okay, so in the practice Q bank, I'm going to go to general chemistry and find the one that we're learning right now. So we're learning stoichiometry, basically. So we're going to give custom instructions, focus on, only give questions for, and I saved them here, gram equivalent weight. We're only getting questions for GEW, GEW, equivalence, normality, and molarity. Give 4 basic questions only. Let's see, it might give 5 just because the way it works here. And then we're just gonna click save and generate. Alright, so there we go. We have 4 successful questions on gram equivalent weight as we asked for. We have successfully got one for equivalence, and then we have successfully got one for normality, and we have successfully got one for molarity. So we're going to do all these practice questions together because a lot of chemistry is a lot of practice questions. So you notice the chemical physical section of this test is a lot of practice. So what is the gram equivalent weight, the GEW of sulfuric acid, when reacting with a diprotic acid in a neutralization reaction? So what you're going to do is you're going to find the molar mass, right? You're going to use the formula molar mass over mole H plus or electron. So we know it's diprotic, right? So if we know it's diprotic, molar mass would be 98 over 2. And then we can always use our calculator. Whoops. So if I bring this calculator up, 98 divided by 2 is 49. So the answer should be 49, right? So let's see. So this one I'm going to strike through. 49, check answer, boom. That's our answer. And if you want to save the answer, the question with the screenshot and everything, you just click the screenshot button here or here. There's actually 2. And then you can save it on your notes. So let's just say, for example, this was my notes. I'll just save it on here. And then I'll have it forever and ever. And then I can, because a lot of kids love using whiteboards now or saving it somewhere. So you can always just copy a screenshot. Okay, so we got that right. Now we're learning about how many equivalents of hydrogen ions provided 12 grams of phosphoric acid, assuming complete dissociation. So we're looking for equivalents of hydrogen ions. So now we need to look for some sort of equivalence formula. Here we have it. It is here. It is mass of the compound over GEW. So first things first, we have to find the GEW. So GEW is 122.5 grams. No, it's not. It's a molar mass. So the molar mass is 98. And the GEW, we're looking for the mole H plus. There's 3 of them. So 3. Okay. And then equivalence of hydrogen ions is mass of the compound. So 122.5 grams over GEW. So 98 divided by 3, 32. So 122 divided by 32, I got 3.8. So let's just see if that was right, right? We want to see if that was right. 3.8. It's not even on here, so maybe we got it wrong. But let's just try. We're going to strike through these because sometimes process of elimination, you might need that, especially for the car section. And there we go. We got the correct answer. Right. So then it gives you the solution here. Sometimes it is important to go through how to get the solution because the number of moles that they got was 1.25 moles of H3PO4, right? So it should have looked more like this. We should have used this formula: moles times the 3 hydrogen atoms, the interest. So this is the way we should have solved the problem. So how we got there is wrong. But that's the point of using this practice bank, is that it tells you not only whether you got the answer right or wrong, but it tells you how you get the correct answer too. So the next one we're learning is normality. So normality is EQ over L, equivalence over L. So that means for normality, you should have learned how to solve for equivalence, which is what we just tried to do, right? So normality with respect to blah, 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 and you can pause and finish that on your own, right? And then this will be your review, right? So for example, I got it wrong, then you want to make sure you really do screenshot the ones you got wrong and then save them somewhere on either, some people like to save it on a spreadsheet, copy and paste it onto a spreadsheet. Some people like to use like Google Docs or something, but you have to save your wrong answer somewhere. So this copy to your clipboard tool or screenshot tool is very important and useful. Okay, now we're going to look at the solution, blah, blah, blah. This is referring to molarity. Molarity. So molarity is this. And you would have to solve for then normality, which is over here, EQ over L over the mole. So then let's say it was this one, which is not. This is how you would have had to do it, and it gives you a step-by-step explanation. So yeah. Awesome. So then you end your block, and that is the end of your practice. And it gives you how much you got correct, how much time you spent doing it, and your overall score. You can also go back and review the explanations. Awesome. So there you go. By this time, you should know kind of how to practice for these formulas. The key thing is you need practice questions, right? So you can just get the practice questions any way you like, really. But the key thing is you have to practice these formulas. It won't be easy at first. So, but the other key thing about these formulas is that you need to learn GEW first before you learn about equivalence, because equivalence involves the calculation of GEW. You need to learn normality and how to calculate normality first before you learn equivalence, because equivalence is literally the numerator of normality over here, right? So you need to learn to calculate equivalence before you calculate normality. You need to learn to calculate normality before you even calculate for molarity. So it's like this build up. So you learn GEW first, equivalence second, normality third, and molarity fourth. And then lastly, going over compound formulas. This is just a definition. So empirical formulas are the simplest whole number ratio of atoms. Molecular formulas are multiple of the empirical formula to show the exact number of atoms of each element. So I'm going to show an example. So here's an example of the empirical formula. Oh, whoops, so here's an example of an empirical formula, P2O5. If you have a molecular formula, so you notice it's simplified. So molecular is 4, P4O10. If I simplify it, I get P2O5. So it's the lowest common denominator, right? Whole number ratio that you can have simplest. So it's the lowest. You want to do practice questions based on this too. Empirical and molecular formulas. So if we go back, we can actually produce them really quickly. So if we go to stoichiometry, just produce only one question of compound and molecular formulas to help me test understanding, and then save and generate. Okay, perfect. So this is exactly what you need. Actually, this is more stoichiometry, isn't it? Oh no, this is good. So this question is exactly what you need. You need to identify the molecular formula in this question. So you need to go over how to find molecular formula, how to find empirical formula. If you are able to find empirical formula, then you're able to find molecular formula, and vice versa. So let's say, for example, I did the question, blah, 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 and I got this answer, right? Then it'll show me a step-by-step explanation and why the key takeaway was, right? Perfect. Okay. Okay, so that was it for chapter 4. We literally went through everything. You want to give yourself probably flashcards for the nomenclature, and then lots of practice questions for equivalence and normality and the compound formulas. So these, okay? You can't just know these definitions and do well on the test. Okay. Okay, so now we're on chemical kinetics, general chemistry 5. Oops. General chemistry 5. Now, the only thing I have to say about this is that we already went through a lot of the types of reactions that occur. The only one we haven't went through since last chapter in unit 4, general chemistry 4, we're on 5 now, and the only one that hasn't been covered is hydrolysis. So you should know hydrolysis is using water to break bonds in a molecule, and then there's an image just underneath it that shows that. So all of these are already went through beforehand, so you should already know what types of reactions are. The main part about chemical kinetics is not about types of reactions, it's about chemical kinetics, so the rate at which your reaction is occurring. So how fast does the reaction occur? And so let's start with, I actually want to give a more structured, in-depth notes on all of these definitions before going into the review sheets. So this is just a regular PDF viewer application, so we're going to look through this and understand what's happening. So first is thermodynamics and kinetic mechanisms. So spontaneity versus speed. So the change in Gibbs free energy delta G tells you if a reaction will occur spontaneously, so when delta G is less than 0, but it says nothing about how fast it happens. So with delta G, you can actually say that delta G, if it was less than 0, then it's spontaneous. If it's more than 0, then it's non-spontaneous, and if it's equal, it's equilibrium. So here's the chart that kind of you can look at, where I just reviewed exactly what I said. So if it's less than 0, spontaneous, more than 0, non-spontaneous, and delta G is equal to 0, then you have equilibrium. Try not to confuse yourself too much. Try to make it simpler while you're studying that stuff. So now we're going over reaction mechanisms. So most reactions do not occur in a single jump. They happen by a sequence of elementary steps. So when I have A plus B to AB, this is one single step. But it says most reactions in real life, basically, they don't occur in that one step. So you're not going to find that happen, right? They happen via a sequence of elementary steps. So reaction mechanisms. So if you go to organic chemistry, you're going to find out that you're going to have not just a simple reaction progress chart where it looks like this. Oops. Where it looks like this. I can draw it out for everyone. Looks like that. Where it's just one reaction. This is 2, right? So it hits 2 transition states. So if you learn about organic chemistry, you'll see that happening as well. There's mostly a sequence that reactions are happening before they lead to the actual product. So there's an intermediate stage there, right? So intermediates are formed. And the intermediates, speaking of intermediates, right? Chemical species produced in one step and consumed in a later step. They do not appear in the overall balanced equation. So when you do a practice question to learn about intermediates, it's really important to remember that your intermediates never show up in the overall balanced equation. Okay, so make sure to do practice questions to help you understand that as well. Make sure to do practice questions to understand how to calculate, or no, sorry, not calculate, for making sure you memorize if delta G is less than 0, spontaneous, whatever, or you could use flashcards for that to help you. The rate determining step is the step that is the slowest elementary step in the mechanism. It acts as the bottleneck, limiting the overall reaction rate. So your rate determining step is whichever one has the higher activation energy. So this one would be the rate determining step. It's going to take really long. It's going to take a lot of energy to get up to its transition state. So this is the rate. This is what we would call, quote unquote, rate determining step. So in other words, RDS, but I never really see the short form. I just call it rate determining step. All right. The next thing is the theoretical models of reaction rates. So these are just theories, right? So you can have of how these molecules are physically reacting with each other to become, something else, right? So what are they doing physically when they're reacting with each other? And so collision theory is a theory where the reactions occur when the molecules physically collide. A collision only leads to a reaction if molecules collide with proper orientation. Proper orientation means they're facing in the right directions with each other, and only when they're colliding in those correct directions or proper orientation and with sufficient kinetic energy, they will overcome the activation energy. So you should know the basics of endergonic and exergonic reactions. You should know this basic chart, this free energy chart. So understand this before you move on. The Arrhenius equation. So the Arrhenius equation is a mathematical framework that links collision frequency, activation energy, and temperature to the rate constant. So if we go to Arrhenius equation in the Mao's down sheet, it's over here. So you want to do practice questions on this for sure. Generate your practice questions, and we'll go through how to do that soon. Trends are important to know. So what this means is that in every formula, you'll notice in the chemical physical section, is that you could tell by the formula of whether one variable, if I change one variable, how will it affect the other variable. So the Arrhenius equation looks like this. Arrhenius equation. Okay, so this is the Arrhenius equation over here. So if K were to go up, then what do you think would happen to A? A would also go up because you could tell by the equation K is equal to A dot dot dot, right? So they're proportional, this is proportional to each other. If we have T go up, then K also goes up. Why? Well, it looks like a trick question because it looks like it's inversely related. It looks like that. It looks like this, 1 over T, like they're inversely related. But no, if K goes up, then T will go up. And if you didn't understand how I explained it, you can just memorize it this way. If A would go up, which is your frequency factor, then K will go up, your rate constant. Frequency factor is how frequent they're colliding. Activation energy is also known as EA. That's a symbol to represent it. And then temperature, T to the rate constant, K. So you should find all those variables here. K, A, EA, R, T. There's also gas constant. This constant you have to be memorized. So 8.3 is the gas constant. Okay. And then transition state theory is a theory where the energy peak of the reaction coordinate diagram. So this is like a reaction coordinate diagram that we had up before. where was it? This one. It's the transition state or activated complex. So this transition state is the highest energy state. It's also called the transition state, and it's also called here activated complex. So what transition state theory focuses on is literally in its name, the activated complex or its transition state, where old bonds are partially breaking and new bonds are partially forming. So what it's saying is that at this peak, this is where the old bonds are breaking and the new bonds are forming to get to the products. Okay, factors that influence reaction speed. So now you have to know what factors will influence a chemical reaction speed. So one of them is the reactant's concentration. So higher concentration increases collision frequency, speeding up the reaction. So as we said before, if you have a higher frequency factor, then K is going to increase, and K is the rate constant. So this is all linked back to the Arrhenius equation. If temperature increases, you increase average molecular kinetic energy. By definition, temperature is your average kinetic energy, right? So if you increase temperature, it will lead to a larger fraction of collisions. So basically your reaction speed goes up, right? Speed increase. Reaction medium, so the state liquids, gas, or solid, and solvent polarity can stabilize or destabilize reactants and transition state, altering the rate. So it depends whether it's liquid, gas, or solid. Catalysts. And that one you would need to do like practice questions to help you understand cues, to help you understand this. Catalysts are substances that speed up reactions by offering an alternative pathway with lower activation energy. So catalysts are often found in biochemistry, they're called enzymes. So those are biological catalysts that we have in our own bodies, which is related to this. Lowering this activation energy, which is from here to here. So calculating activation energy looks like this. Right? So from here to here is the activation energy, right? So you can calculate it if you ever have to doing that. So if they give you number here and they give you number from here, you find the difference, right? Okay. And then it says homogeneous is the same physical phase as reactants, and example, all aqueous. So what does that mean? If you have homogeneous catalysts, then it's the same physical phase. So gas and gas, liquid and liquid, solid and solid. Heterogeneous, different physical phase from reactant. Solid metal surface with gaseous reaction. So think of homo is same, and then hetero is different. All right. And now we're going on to rate laws and reaction orders, which is on here on the mile down sheet. So this rate and reaction orders on the mile down sheet looks very intimidating. But how you can learn it is by following me. There's an easier way to learn rate laws and reaction orders. So rate is equal to K-A-X B-Y. And it looks complicated, but it's not. So basically what happens is reaction rates are tracked by rate of product formation or reactant disappearance. Experimental rate laws follow the general equation. So the main thing you have to know is that whenever you get a practice question, and you'll learn this by doing your practice questions enough, that rate cannot be determined non-experimentally. It's going to be determined experimentally. So you're going to be given data in a practice problem. They're going to give you experimental data, and using that data, you input the numbers into this rate law, and then it will let you find the order, the rate orders. Rate orders would be over here in the chart. It's also here. And so when you solve for the rate law, if you get R equals K, where basically you get A0, this is your exponent laws. So if you don't know your exponent laws, then you should know that anything to the power of 0 is 1, right? So if you substitute K, A, 0, you're going to get K times 1. What is K times 1? Just K. So your rate laws, rate equals K. Rate for this one is KA1. Didn't show the 1, but it's basically there. Sometimes in math, they don't show the ones just because it's simpler to write. And then KA2. This is the second order, right? So I think that makes sense. So you could tell K is 0 for, oh wait, not K is 0. That's wrong, not like that. K, whoops, how did I get this? Undo KA0, like that. Okay, so that's how it works. And then you want to do a rate law question. Rate law practice problem. So I'm going to show you how to find the practice problem from here. So if I go to practice QBank and then, oh darn. Okay, so I believe we stopped on these rate orders. So again, if your 0 order, rate equals K when you solve for the rate law. So then the graph will look like this. So if you ever see a diagram, you have to be able to know what a 0th order slope looks like. And it even tells you here's slope. And then you have to know what a first order reaction looks like. and then you would have to know what a second order reaction looks like. So these are the trends of what they look like graphically. So you have to understand that they look like this. So then we're gonna, so the linear integrated plot. So in other words, the linear plot. So in other words, just like this linear type of diagram, what kind of trends, that the one we were just looking at, what is it? Slope is negative k. For these two, as we saw, 0 in first order, as you can see, they're negative k, slope equals negative k, and then slope equals positive k for second order. I mean, yeah, positive k for second order. So as you can see here, it's going up in a positive direction. This is negative, going down, down, this one's going up. All right, so that's, and then you'll notice on the graph that all of them, what they all have in common with their x-axis is time. So if I just remove all these bad annotations I just made, this is your x-axis, this is your time, and the y-axis is different for each of them. So your y-axis for your 0th order is just the concentration of A. This one is ln times A. This one is 1 over A reciprocal. So like, you don't really have to, you can memorize this, but you don't really have to know like too many specifics about why, but you should memorize that, you know, this is what happens in second order, this is what happens in first order, this is what happens on 0th order. So with 0th order, you get constant speed unaffected by concentration. That is actually very important. Only changed by temperature or catalyst. So the reason why it's unaffected by concentration is because if Ka is to the power 0, then no matter what number I substitute here into A, it's always going to equal to 1 because it's to the power 0. So K will always be K times 1 is equal to K. So it will simplify to rate equals K. So that's why concentration, no matter how much we change the number of A, it's not going to matter because it won't change the rate. All right. And this is also important here. Rate is directly proportional to concentration. So in this case, you could see that the rate of reaction is directly proportional. So if rate goes up, reaction rate goes up, RTE, or ATE is proportional. If rate goes up, then your, concentration will also go up. Or if your concentration goes up, then your rate will also go up in a first order. Second order depends quadratically on concentration. Okay. Now, the last but not least is knowing special rate orders. It's not very high yield, but it's important to know that you could have a broken order where there's fractional rate orders, like you have a fraction over here. You can also have a mixed order where apparent order changes over time or across different concentration regimes is common in enzyme kinetics. So mixed order reactions. A mixed order reaction is a chemical reaction where the reaction order changes as the reaction progresses or the concentrations change. Okay, so that is mixed order, which is not even mentioned on here. Apparently, the units are also important to know. These are just memory based and then also practice problem based. So once you do enough practice problems, you will start to understand all of this way better. But I went through most of the basics. And then it is the equations. So equations, reaction order and Michael-Mentel's curve. This is the Michael-Mentel's curve where basically Michaelis-Menten curve, my bad. At low substrate concentrations, the reaction is approximately first order. At high substrate concentration, the reaction is approximately 0 order since the reaction ceases to depend on the substrate concentration. So if you have a high substrate concentration, so what you need to know about the Michael-Mentel's curve is exactly this. This is exactly what you need to know. It's literally in this picture here. As the image suggests, the rate order reaction depends on the concentration of the substrate. Vmax is da da da. So this is also related to enzymes, as I was saying before. And the Michael-Mentel's curve, here's the first order region, and here's the 0 order region, as it was saying in the review sheet that we had here. So that's what I was saying here. So what's interesting is that the Michaelis-Menten curve here is basically like, all right, that's all. Okay, that's all we had to know about Michael-Mentel's curve here. So the Arrhenius equation is repeated twice. It's also down here, so you don't have to go over it again. So we went over it already. Definition of rate. So rate, you should know how to calculate for rate when you're given this scenario. So if you have a reaction, it will look like this. Reaction AA plus BB is to CC plus DD. So this is how you can solve for it. So when you do your practice problems, I keep saying to do them, but it's so very important. That's the only way you'll understand how to calculate. if you know your basics of math, it should be fairly simple for you. If you don't know what delta means, it means the difference of, right? So the difference of like usually it's starting like initial value versus final value. So you might want to, if you don't have a math foundations, you will need to understand a little bit of math, but it won't be hard at all. This is nothing like calculus. There's no calculus on this exam. It's just basic mathematics. So I would recommend reviewing math if it helps you, right? And which it would. In chem, it's just basic subtraction and things like that, addition, multiplication, right? And exponent laws, as you start to see here with having some exponents here. And the rate law, of course, is so very important. Doing rate law practice problems are very, very important. And then radioactive decay is over here as well. And then, yeah, so we already went over reaction mechanisms. So as I said earlier, usually reactions aren't just A plus B gives you AB. Reactions are, here's the overall reaction. But reactions can come in like in terms of steps. So you have step 1 and step 2, right? So this is your intermediate. Sorry. So A to B is intermediate as it says here. So literally this is your intermediate, and then you get your final product 2AB in your overall reaction, right? So the first one here required a lot of activation energy, so it's the slowest one, and then this is the faster. Step 2 is the faster one. It's not always the case that step 1 is necessarily the slower one or the rate determining step. Remember that. As it says right here, it says that the slow step is the rate determining step. So that's so we already went over that, so check mark. And then lastly is Gibbs free energy, where the EA minus EA reverse of the reaction gives you delta G. So that's one of the formulas for delta G. There's actually quite a bit of formulas for delta G to know, but this is just one of them. And when you do your practice problems, you get to understand that more. I already showed you how to generate them for the last question. Yeah, you know what? I'll try to give free ones here. Let's see. General 5 chemical kinetics. So let's say I wrote, so let's say I wanted to really practice my rate law and Arrhenius equation. Give me 2 questions, rate law and Arrhenius equation questions, and then save and generate set. Okay, so now you're given this data here. This is actually really good to practice this way. So you have your data here, and you want to find the rate. So you're looking at this, you're wondering, I never learned this. Well, it's because the rate law over here, where's the actual practice question? Over here, it's right here, underneath all of this. It's right here. So we're using this equation to help us solve for this. So rate is equal to KAX times BY, right? So our job is to find the rate based on this experimental data. So the initial rate of formation of product C for the reaction 2A 2A plus B to C plus D was measured at about 300 Kelvin using different blah, blah, blah. So automatically what you want to use is the rate law. What is the rate law for this reaction? So what you're going to do, well, you could just take a picture and then paste this into your notes and start solving. Or if you're doing with pen and paper, that's fine too. You don't have to paste it then. Saves you a step, I guess. So what you're going to do is you're going to look for a constant. So here in trial 1, we have this constants. And then here in trial 2, we have these. And here in trial 3, we have these. Right? So we want to find A and we want to find for B. A and for B. Right? So because that's what we have here. And so we want to know the rate. So in this scenario, we have a constant for A and then B. So we could do the difference here to find the rate of A. So to be able to do that, you need to calculate for the difference. And that will give you that. So you're going to compare trial 1 and trial 2. So what you do is, sorry, you don't subtract, but you divide. So it's not the difference. My bad for that. 8 times 10 to negative 3 2 times 10 to negative 3. So this is how I learned to do it. So basically, we're going to divide the trials, and then that will give me 0.24 times 10, 0. So that gives me 1. So 0.2 times 1. Or whoops, 0.2. Whoops, that was wrong. So now, this is 4 times 1. Oh, whoops. Yeah, we can do it like that. That's fine. 4 equals 2x. So we're going to do it step by step using the exact solution that was given, which is actually a really good solution. So here we have order with the respect of A. So we're trying, like I said, we're trying to find A and then B. So we're going to do A first. So we're finding A, compare trial 1 and 2. Why did they choose 1 and 2? Because for 1, it's all constant, 0.1 initial, 0.1 initial for A. And the only one that's changing is A for 2. So that makes it good to compare those two, where B is held constant and where A doubles. So they're actually explaining why they chose trial 1 and 2 to compare, to find reactant A. The rate increases from 2 times 10 to the negative 3 to 8, right? So 2 to 8, okay? Which is a 4-fold increase. So what you can do is you can find the ratio 2, or you can do it this way, 8, 2 times 10 to the negative 3 times 10 to the negative 3. That is 2 times 10, 0. 2 times 1 is just 2. And so what you do, and then you do 0.2 divided by 0.1 equals 0. Oops, calculator. 0.2 divided by 0.1 is 2. So you get 2 equals 2. Sorry, this is 4. My bad. See, we all make mistakes, guys. This is 4. Sorry, it's too late at night. This is 4. So right here is 4. So you get 4, 4. And then what you want to do is you take this number here, 2, and you want to figure out 2 to the power of what will give you 4. Okay? So 2 to the power of what will give you 4? 2 to the power of 2 should give you 4. So that's what they got here. So x should equal, the x here should equal 2, which means your A is to the power of 2, which means that we could cross out this answer, so A and C can get crossed out. So you go on this cubic here, you cross out A and C, and then we'll have B and D left over. So now we have to solve for B. So let's do that second. So now we're going to follow the solution because it was a good solution. We're going to follow it out. So with respect to B, they're going to compare trial 1 and 3. So let's remove, okay, I don't think I'm allowed to remove that. There's no layers on this thing. Okay, I'm comparing 1 and 3, sorry, not 2 and 3, because we want a constant, right? So nothing else is changing but B, right? So only B is changing. A is not changing. 0.1 to 0.1. This one is 0.1, 0.3. And this one was, I can't even see it anymore, 2.2 times 10 to the negative 3 to 6 times 10 to the negative 3. So what we're going to do now is the same thing. So compare trial 1 and 3, good, we went over that. We went over that A was constant and B was tripling in concentration. And then I went over the rate increases. So let's go over how they got to this number exactly, y equals 1. So we want to solve for B, y. That's what we're looking for, right? So let's go over how to do that. So in initial B versus this one, so you have 0.3 divided by 0.1, and then you have, actually, sorry, let me do it the other way around. Or actually, no, that's good. 0.3 divided by 0.1, and let's do the ratio for this one, 6 times 10 to the negative 3, and then do 2 times 10 to the negative 3, and that should give you 3 times 10, 0 is not equal, sorry. And then this should give you, if you put in the calculator, 0.3 divided by 0.1 gives you 3. So this should be 3, right? So this gives you 3, and this gives you 3, 3, and 3. So you have 3 and 3. That makes it easy. Oh, by the way, this is 3 times 10 to the 0 is just 1. So you get 3 and 3, like I said earlier. I just wanted to show the steps. And then you want to know, okay, 3y is equal to 3. So then we have to solve for y. 3 to the power of what will equal 3? 3 to the power 1 will equal 3. So therefore, y is equal to 3. And that's how they got y is, sorry, not y equals 3. Y is equal to 1, sorry, I wrote it here. Y is equal to 1 because 3 to the power of 1 is 3. So we solve for by. So now we know b is 1, 1. So then we can cross out this answer choice D. So we go back to the Q bank, cross that out, answer choice D, and B should be the correct one. Hopefully it is. There you go. So that's the correct one, and it shows you how to go through the solution. Awesome. So now the next one, I wanted to go over the Arrhenius equation because it's another high yield. So you want to read through it. Catalyze blah 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 has a specific activation energy, proceeds with a rate constant K at 37 degrees Celsius. Which of the following best describes the effect of the enzyme on blah 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 blah. So to be able to know, whoa, what happened? See, you're gonna see glitches like this because we're still developing the application to be better. I don't know what happened here even. But you basically want to use the Arrhenius equation to solve for this. I'm not going to go too in detail because the way you learn it is through doing it yourself. But it shows you exactly all of that. So I'll just paste it here so that people can use this for free. So here's the second one on Arrhenius equation. Here, I'll just delete this. You can pause a video here and do this question here without looking at the answer. Or you could look at the answer, but don't look at the solution quite yet. You want to focus on the how. How did I get the right answer, not just what is the right answer. That's really important. Okay, so all of that is done for chemical kinetics. Now we're going to move on to equilibrium. It's hard to read here, but I'm pretty sure it says equilibrium. This is now in chapter 6. So equilibrium constant. So this is another way to write the reaction. These give you, like, these little a, little b, little c, gives you like theoretical mole numbers. So if it said 2a plus 3b, then this is theoretically like 2 moles of A, 3 moles of B, according to this stoichiometry, right? So KEQ, this is the formula for KEQ. And you notice that the formula for KEQ is the same for the reaction quotient, otherwise known as QC. And the reason for this is because, and you have to exclude pure solids and liquids. So the reason for this, why KEQ is also the same formula for the reaction quotient and vice versa, is because basically it's looking for the same thing but at a different time, right? So KEQ is looking at what's happening at equilibrium, but QC is not looking at equilibrium, not at equilibrium. So then what exactly is KEQ and reaction, oops. So now the question comes, what exactly is KEQ and the reaction quotient looking for? Well, KEQ and the reaction quotient look for the ratio of products to the reactants in a chemical equation. So if I solve for this, both of them, I'm surprised they didn't show the simplified formula, but basically for both KEQ and even reaction quotient, QC, is equal to, what's it, reactants, right? Is equal to, yeah, reactants over products. And I hope you could see that because you'll notice, or sorry, products over reactants. No, I was wrong. It's products over reactants. Products over reactants. Because if you notice here, only the products are in the numerator here. Only C and D. And then the reactants are in the denominator. So that's a way to help memorize it. So that's what it's trying to look for. At KEQ just means at equilibrium, what is the ratio of products and reactants? At reaction quotient is what's the ratio, but what's the ratio of something that was not at equilibrium, right? And so these, you also have to make sure you exclude pure solids and liquids, which is where practice problems come in to help you learn this part, because this is important not to get this wrong when you're doing your practice. Because it's very easy to see a reaction and go like, oh, the formula told me put C here, D here, A here, and B here, right? But if, let's say, B was a solid, you have to remember not to put it there then. So you don't add that to the equation. You just do your regular C, C, D, D here, and then A. But you don't add B because it's a solid. So that's what it means by exclude pure solids and liquids. You need to not add those when you're solving for it. Remember that when you do your practice questions. Okay, and then we're gonna go into reaction quotient since we were talking about it anyway. So if Q, the reason why it's important to know reaction quotient and equilibrium is that like you need to know them relative to each other because that will tell you something. They don't tell you much alone, but they tell you something when they're especially for reaction quotient. It tells you something when it's compared to KEQ, and when Q is less than KEQ, then your reaction delta G is less than 0. Which means your reaction is right. Okay, what does that mean? Well, that has to be explained with the Le Chatelier's principle, which I'll go into soon. So when Q equals KEQ, you're at equilibrium. At this point, we should know what that means. When Q is greater than KEQ, then your delta G, or your Gibbs free, we learned Gibbs free over here, is greater than 0. Your reaction is left. What does that mean? Left, shifting left or shifting right. What does it mean to, they literally, in terminology, people will say, I should remove this now. People will say reaction shifts to left, or people might say reaction shifts to right. Okay, so if the reaction is shifting left versus right, we can explain this using what we call Le Chatelier's principle. I didn't spell it right, but we'll go into what that is right now. But this principle is going to explain this right now. So for the Le Chatelier's principle, I'm just going to remove this other stuff. Let's say, okay, they gave an example here, which you don't really have to know right now, but basically, if I have one thing on this side, like if I have this, if I increase whatever is here on this side, if I increase whatever is here on this side, um, the reaction will naturally start to increase on this side to balance it. It's like a seesaw, right? So if I have A, B here, and then I add even more, so I have a lot here, but very little here, where the reaction is going to start to shift rightward to the right side so that it would be equal, like a seesaw. And the opposite is true for shifting the reaction left. So your body uses this bicarbonate buffer system, by the way. So you probably want to follow through with this. So CO2 and water form carbonic acid, which is right here. Carbonic acid breaks down into bicarbonate acid with the H plus ions, hydrogen ions. And hydrogen ions control the acidity or pH of the blood. So this is what controls these hydrogen ions here, right? So if I add acid, right? If I add acid, extra acid enters the blood. So this is going up, right? If this is going up, then the concentration of H plus goes up. So that's what that means. Extra acid, this is going up. So the Chatelier's principle states that the system will shift to use up the extra H plus, right? So the reaction then moves to the left because there's an upward trend on the right side. Like I said, it's a seesaw. If it's higher on the right side, then it wants to shift to the left on this side to balance that out, right? And so adding a base is the opposite. So when a base is added to the blood, it removes this. So then if it removes this side, then we have to shift the reaction right so that this side can be at equilibrium. Or yeah. So that's basically how the bicarbonate system is related to Le Chatelier's principle, or in other words, how the Le Chatelier's principle is able to explain the bicarbonate buffer system. Okay, so now we're on thermochemistry. So thermochemistry is about systems and processes. So you will have a system, which is anything that you are observing. I'm surprised they didn't really give you definition for system and processes on the review sheet, but you should know basically systems is what you're observing, and processes are things that happen to the system. So if the system is undergoing any change, we would call that a process. It's going through a process. So systems and processes. So in an isolated system, let's see if I can zoom in a little so it's easier to see. All right, so in an isolated system, it exchanges neither matter or energy with its environment. So systems interact with their environment, right? So environment is anything outside of the system. So that's another key term to know because they define environment like in that way. A closed system is when you can exchange energy but not matter with the environment, and an open system is when you can exchange both energy and matter. So you should know to be able to tell the difference between isolated system, closed system, and open system and study these terms together and do your practice questions for those. So you can test yourself on whether you actually understand the differences and can differentiate in real life circumstance. Isothermal process is when the process, everything can change, but it's constant in pressure though, okay? An adiabatic process is it exchanges no heat with environment. An isobaric process is constant pressure. And isovolumetric means constant volume. It's also known in brackets as isochoric. So those are systems and processes. Temperature and heat, we're going to go through this first. So temperature is different from heat. So T is different from heat. And in a lot of formulas, heat is represented by the Q. A lot of formulas, temperature is represented by T. And it's a scale measure for temperature is the average kinetic energy of a substance. Celsius versus Fahrenheit. So I'm sure you heard of Celsius or Fahrenheit wherever you live to describe weather. But yeah, so 0 degrees Celsius is equal to 32 Fahrenheit, freezing point for water. Room temperature is this. body temperature is this, so you should know this. And then you should also know how to convert Fahrenheit to Celsius and Celsius to Fahrenheit, but more so probably Fahrenheit to Celsius, because then Celsius can then be transferred to Kelvin, which is an SI unit, right? So Kelvin is another unit for temperature, right? And heat is different from temperature. Heat is a transfer of energy that results from differences of temperature. So when hot transfers to cold, you're going to have a transfer of energy. So whenever a hot thing is combining with something that's cold, the hot will transfer its energy to the cold, and that's why the cold raises in temperature eventually, trying to hit equilibrium. We love equilibrium. And now we're on states and state functions. So what is a state function? State functions describe the physical properties of an equilibrium state. They are pathway independent: pressure, density, temp, volume, enthalpy, internal Gibbs free energy, and entropy. So in other words, P for pressure, this little p is for density, D is not for density, T is for temperature. If you ever see them in formulas, these are what the variables usually look like. V is big V for volume. Enthalpy is usually H, big H. Internal energy is usually U, I believe. Gibbs free energy, we've seen that multiple times. We've seen it as delta G, but alone it's just G, right? And entropy is S, as we see right down here. And enthalpy is H, as we see in this box. So all of these, P, little p, T, V, H, U, G, S, all of these pressure, density, blah, 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 all of them here are state functions. So they are pathway independent. So it doesn't matter how you get there, it matters where they are right now. So that's why they call it a state function. Standard conditions is this. You need to memorize that standard condition is 298 Kelvin at 1 atm and 1 mole. Molarity, I think, big M. Note that in gas law calculations, let me just make sure. So I wanted to quickly go over the difference between standard conditions versus STP, because they are different. So STP is standard temperature and pressure, and general standard conditions, often meaning standard state conditions in thermochemistry, differ mainly in their baseline temperatures and intended uses. So STP is for gas laws, and that's when you have 0 degrees Celsius, while standard thermodynamic conditions, which is the one we just looked at and we're reviewing for thermochemistry, uses 25 degrees Celsius for energy calculation. So they are different. So you have to memorize the differences. So when we use gas laws, and you'll see soon in chapter something about gases and ideal gases, STP is different from standard conditions. Just to make it clear, 1m stands for 1 molar, which is the concentration of molarity. All right, so we should know molarity from our, I think, unit 3 on stoichiometry. So yeah, and STP is actually mentioned here. Okay, fusion is when a solid turns into liquid. Freezing is when liquid turns into a solid. I'm sure you can think of real life examples in your own life. Vaporization is when a liquid turns to gas. Sublimation is when a solid turns to gas. Deposition is when a gas turns to solid. And a triple point is on this phase diagram here. It's probably hard to see in dark mode, so I put in light mode, and this is your triple point over here. And the triple point is basically where all three phases exist. A supercritical fluid is when the density of gas equals the density of liquid, so no distinction between the phases. So you could just memorize these kind of, not this one, but you can memorize where it's located on this graph here. So you should know how to read this graph or what it's trying to say. Other key points is also critical point, and supercritical fluid is right there. Gas, triple point, liquid happens here, solid. So this is your pressure on your y-axis, and this is your temperature. Okay, and now we're gonna go back into dark mode because it hurts my eyes. Now we're gonna go into entropy. Where's enthalpy? Where did that go? Okay, we'll go into enthalpy first and then entropy. So enthalpy is a measure of potential energy of a system found in intermolecular attractions and chemical bonds. So it's a measure of potential energy of a system. And so when phase changes happen, they're endothermic because gas has more heat energy than liquids, and liquids have more heat energy than solids. So not just any phase change. It means when a solid is turning to a liquid and when a liquid is turning to gas, that is endothermic. All right. You could think of it this way, is that when you're breaking bonds, you have an endothermic reaction. But if it's exothermic, releasing heat, right? Exothermic reactions release heat by definition. Then basically you have gas to liquid, liquid to solid. All these are exothermic, because you can think of it like exothermic is having bonds being formed. So they're getting closer together. And when a solid is, so when gas is turning to liquid, they're getting more bonded, closer together. Think of it that way. Liquids are then becoming solids, and now they're even more closer together. So it's exothermic, right? Hess's law. Hess's law is an important law, and it's basically that enthalpy changes are additive. So if someone gave you H1 of one reaction and H2 of another one, you can solve and add them together to get the total enthalpy, total H of the reaction. So you want to do practice questions for this, and I can't stress it enough to practice questions to do many practice questions for Hess's law as possible. Okay, and then we have entropy. Entropy is a measure of the degree to which energy has been spread throughout a system or been between a system and its surroundings. So you want to memorize this formula here. It involves knowing that delta S is equal to Q rev T. Okay, that sounds weird, right? But basically it's saying that the difference in entropy is equal to heat from the reversed reaction, heat over temperature. And so you want to do practice problems to practice this in context so that it makes more sense. Standard entropy of reaction is delta S standard equals products minus reactants. So all of them, if you notice, for delta H reaction for heat formations, sometimes people might do HF to show heat formations. It's basically saying the same thing. Is products minus reactants. Entropy is maximized at equilibrium. Okay, and then we have Gibbs free energy. They've been going, there's so much to go over Gibbs free energy. That's how high yield Gibbs free energy is. Everything, to know everything is pretty high yield, but Gibbs free energy is especially high yield, and there's a lot of formulas to know about it. So we already went through this before, that delta G less than 0 spontaneous, blah, blah, equals 0. So yeah, so we already went through this beforehand, so you don't have to go over it again. One thing you want to understand is this formula here. So once you understand enthalpy and entropy, delta G is a combination of, it's derived from, as it writes here, derived from enthalpy and entropy, and it also takes in consideration temperature. So now we need to understand this equation a little bit more, and it's written again twice, like over here as well. So to go over this, basically what you have to know is that at high temperatures, so let's say we had high temperature on this side, what would happen? What would happen? This number is really high, and this number is kind of low-ish. If you have a positive H here, if you have a positive minus another positive, it's only at high temperatures that delta G is spontaneous. Okay, if this is positive, but this is negative, then you're always non-spontaneous because delta G is going to be greater than 0, because this number is really positive. This number is less than this number. So let's say you have 3 minus 1. That's basically the situation. You get 2, right? Now delta G is greater than 0. So this pretend delta G is equal to 2. So that's non-spontaneous at all temps with this combination together. With this combination together, right, you have spontaneous at all temps. So what I recommend is kind of working this out by substituting your own numbers to try to see how this works. Negative and negative, you're spontaneous at low temps. No temperature dependent when delta H and delta S have the same sign. So now we could go over standard Gibbs free energy reaction, which is also products minus reactants of delta G. Okay, and now we can go over from equilibrium constant. So you can also find the delta G of the reaction from the equilibrium constant. So this is a constant here, R, and then T and ln there. So you need to know how to use this. And then from reaction coefficient, you also need to know how to use this too. And this K, EQ, and Q, we already learned before. Remember over here in chapter 6 on equilibrium. So this applies down here to know what KEQ is and Q is. So everything builds on each other. If you don't know the previous, then you're not going to know what you're doing to the next. So it's good to master things in steps, and I'm just showing you what those steps are instead of jumping right to the end, getting confused, and then going to the middle, and then getting confused, and then going back to, I don't know, just wasting too many times instead of following a straight path to, I would say, more happier completion, because you're not getting as confused. Okay, so now let's go into quickly the gas phase, chapter 8. So there's a whole physical understanding of gases, right? So gases, there's ideal gases. So I'm going to put gas. There's ideal gases and there's real gases. All right, so now, okay, so I just took a small break, water break. Okay, so I just went and took a small water break, and now we're back to ideal gases and real gases. So an ideal gas is a theoretical gas. It's theory, right? It's not a real gas, it's just theory, whose molecules occupy negligible space and whose collisions are perfectly elastic. Gases behave ideally under reasonably high temperatures and low pressure. This is actually high yield and important here. So this part. Ideal gases, reasonably high temperatures and low pressures. Memorize that. Memorize this. So STP, as I mentioned, memorize that. 1 mole of gas, STP is equal to 22.4 liters. This will be very important to you. 22.4 liters will be very important for you to memorize this, as when you do practice problems, you might have to know and put in the volume, and in which case the volume would be 22.4 at STP, right? So when you do ideal equations and stuff and other equations, you have to know those. Units, these are important too. So 1 ATM, so these are units of pressure, is equal to 760 mmHg or 760 torr or 101 kPa or 14.7 psi. I have personally seen ATM and mmHg. I have not seen torr yet in my practice questions. kPa I've seen before. PSI I haven't necessarily seen before, but you would have to know definitely these two for sure. I'm pretty sure it's written from high yield to low yield. So basically, you need to know that pressure at STP is 1 ATM for sure. And these other ones too, if you could, at least like up to here, and PSI. You know what, just know them all. Real gases deviate from ideal behavior. It would be the opposite of what we have here. So ideal gases was it loves to be at high temperatures, low pressures, and it's the opposite for real gases because they're deviating from ideal pressure, right? So it's the opposite, low temperature and high pressure in those environments. So at moderately high pressure, low volume, or low temperature, real gases will occupy less volume than predicted by ideal gas law. So this is your ideal gas law down here, because particles have intermolecular attractions. At extremely high pressure, low volume, or low temperature, real gases will occupy more volume than predicted by ideal gas law because the particles occupy physical space. So you should know this. You should know in what environment will happen to the gas, to the real gas, right? And then van der Waals equation of state is just one way to predict the deviation that's happening. So real gases deviate from being an ideal gas under these circumstances, right? And this equation is just one way. So this equation, I have not had to use this entire equation before, and I don't think you have to. You should memorize, but not really to the point where you know how to calculate for it. This one, you shouldn't have to calculate. I haven't had to calculate it before in practice problems, but you should know what means what. So A is a correction for attractive forces, and B, so A was over here, and B, it corrects for volume of the particles themselves. So I like to think of it as size and then the intermolecular intermolecular bonds here. Okay, so in ideal gas law, R is equal to 8.31 joules per mol K. You need to remember this constant. Density of gas, this is the formula to memorize. Everything gets easier when you memorize these formulas, by the way. Combined gas law is right here. If you rearrange it, you get this, and oftentimes you will have to rearrange to get this, right? So if you don't know how to rearrange, or you think it'll take too long on the test, just memorize this rearranged formula. That will help you. And then Avogadro's principle. These are that. Boyle's law, PV. So Avogadro's principle is the mole over volume equal to, so usually it's initial versus final. Mole versus volume here. Pressure volume equals K, or PV equals PV. So initial pressure and volume, for example, is equal to the final pressure volume changes, and they change proportionally. So yeah. So that's Boyle's law. And then Charles' law is the volume and temperature. How do those relate? Gay-Lussac's law is this. And so once you do enough practice questions, you get used to it. But most of these are just memorize. And then the practice is really easy for this because the math is really easy for this. It's just basic division, multiplication, right? Multiplication and division. So that's why I didn't highlight that you have to practice it too much. You do have to memorize the formulas though. So this is more memory based than practice based in my opinion. But if you are having trouble with the math, then I would be surprised because it is kind of more basic, just multiplication, division, rearranging, and to solve for the variable that the problem is looking for. Other gas laws, Dalton's law is important. So in Dalton's law is that you can find the total pressure of a gas based on the sum of all its partial pressure, all of partial pressures. So yeah, the problem might give you that. The practice problems of Dalton law can also be finding partial pressure from mole fraction. Mole fraction. I'm not sure if we went over mole fraction in this before in stoichiometry, but if you don't know mole fraction, it actually shows up again. Where's mole fraction? Here, it shows up again when you're doing chapter 9 on solutions. It shows up over here. Moles of solute over total moles of the solution. By the way. So yeah, that's X. So you have to multiply X by P, which is the total pressure, and that will give you a partial pressure if you ever had to find it that way. And then Henry's law is basically about the concentration. Sometimes I've seen people use C to represent concentration. Anyways, it's just a way to represent it, but this one's using A equals A. how concentration changes lead to also have a difference in pressure and change in K. So K. Okay, so one thing I want to highlight about Henry's law is this KH right here. This is nothing to do with rate or anything like that. This is a constant. This is a constant, okay? So that constant is usually given to you during the practice problems, and if it's not, then you could solve for it this way. Yeah, the K's in these ones are also representative of the constant. But it's not like rate or anything like that. Okay, now we can go into kinetic molecular theory. I didn't really review this as much when I was reviewing, so this is but it's still important to know kinetic molecular theory. So Ke is half mv squared, and if you did a physics review already, you would know that this is just a kinetic energy formula, right? Is equal to, this is a little bit new, kBt, right? So basically, kb is a constant here, and you would memorize that. And so Ke is proportional to T. So if your average kinetic energy, and you should know this by now, that if average kinetic energy goes up, then temperature goes up, because temperature by definition is your basically average kinetic energy of the molecules. So if that's going up, then kinetic energy is going up. If you increase molar mass, the molecules move slower. So this is related as well here. Speed, root mean square speed. So let's say you have particles that are trying to diffuse from an area of high concentration to an area of low concentration. That's diffusion, or effusion even, the movement of gas from one compartment to other through a small opening. So let's say I had this tiny opening and there was gas on this side, and to go through it, that's effusion. And so Graham's law kind of helps you mathematically realize that if you have low molar mass, it would diffuse or effuse faster. But if you had high molar mass, then you get diffuse or effusion going slower. So let's say you have helium or something like that, or I don't know, hydrogen. It's hydrogen at 1. It's been a bit for me. A hydrogen or something, and then you had something heavier is equal to R1, R2. And let's say the question gave you R1, or let's say the question gave you R2 even. Actually, never mind. So it's important to do Graham's law to understand it better through a practice questions as well. Do practice questions for root square speed as well. And then now we have diatomic gases. So this is a little bit too much. There's too much stuff here. So for diatomic gases, they can exist as diatomic molecules, never stand alone atoms. So that is have no fear of ice cold beer. So I've already shown this before. I've shown this before at the beginning explaining the periodic table. So we're good on that, hopefully. All right, and this is where you would find on the periodic table. So have no fear of ice cold beer. So that should help you memorize the 7 diatomic gases. All right, terminology for solutions. Okay, so now we're going to go over general chemistry 9 solutions. So solution is a homogeneous mixture of solvent particles and solute. So you have solute and solvent, right? So you should know those two terms. They're very important. Via electrostatic interactions. So that's also important. Solvation or dissolution, the process of dissolving a solute into a solvent. So the solute will dissolve into a solvent, such as if I put salt into water, salt is my solute and water is my solvent. Most of dissolutions are endothermic, although dissolution of gas into liquid is exothermic. Solubility is the maximum amount that the solute can be dissolved in a solute at a given temp, and molar solubility is the molarity of the solute at saturation. Complex ions are when you have cation bonded. So cation would be in the middle, right? And then there's like ligands that come out of it, like a spider. Not really, but ligands, which is the electron pair donor, and it is held together with coordinate covalent bonds. Should have known what coordinate covalent bonds are since I think chapter 2 on bondings, or was it 3.2, I think. Formation of complex ions increase solubility. Okay, because of the ligands, by the way, because of the ligands. Solubility in water, polar molecules with positive negative charge are attracted to water molecules with hydrophilic. Hydrophilic means it wants to affiliate with water and it wants to come together with it. And non-polar molecules are repelled by water and hydrophobic. So hydrophobic, think of it as it has nothing wanting to do with water, so it's repelling water. But hydrophilic is it wants to be with water, so it's attracted to water. Okay, now solubility rules is just pure memorization. So you just memorize that this, except this, is soluble in and then this is insoluble in water, I think, right? So yeah, it's just memory. And then concentration, this is really high yield, very important to practice, and it might take a lot of your time, to be honest, just practicing doing this. This is like stoichiometry too, as well. So yeah, you need to memorize these equations, be able to use them for practice problems. Yeah, and I would recommend probably doing it stepwise and making sure that if you don't understand how to calculate, for example, equivalence, then you go back to chapter and re-understand how to calculate for equivalence. Okay, and now we're looking at solutions equilibria, which is basically where you have saturated solutions are in equilibrium at a particular temperature. So I have to go over, I don't know why it's not even on here, but it should be going over, why is this my measure? We should be going over what saturated solution is, what unsaturated solution is, and one at equilibrium. So equilibrium is basically you have your salt plus water, right? And it's dissolved nicely, fully. And then in a saturated solution, it's dissolved, but now you have too much salt. So what happens? Precipitate forms. So stuff, you know, when salt stays stuck at the bottom, super saturated. Oh, sorry, it's saturated at equilibrium. Let me change that. Equilibrium equals saturated. Dissolved nicely and fully, right? Saturated. But if you have super saturated, right? Then you get dissolved, but it's too much of the solute. So you get precipitate. So solute forms at the bottom, not fully dissolving because super saturated, right? And then unsaturated solution. I don't know where this is on the review sheet, but it's not even on here, which it should be. Yeah, it should be on here. And then unsaturated is when basically you have the basically it's very dilute. That's how I would describe it. Like there's more solvent and there's still space for more solute to kind of saturate. I don't know how to explain it right. Kind of like there's more space for salt, for example, like a solute to go into the water and dissolve, right? So it's unsaturated. Okay, so you can also know the solubility product constant is KSP, right? So KSP is the equilibrium expression for something that dissolves. This is actually basically KEQ that we learned beforehand. And IP, ion product, is basically analogous to the what was it called again? Quotient, reaction quotient. It's just using a different term. It's using solubility product constant KSP, but KSP is basically KEQ, and IP, ion product, is basically a reaction quotient. So you like we did with KEQ and Q reaction quotient is you have to compare them relative to each other for them to have some meaning. So this is how they compare. If IP is less than KSP, it's unsaturated. If they're equal, it's equilibrium. If IP is greater than KSP, it's supersaturated and precipitate will form. So just to go back to KEQ to make sure everyone knows, that was in chapter 6 on reaction quotient, and it was over here, right? So you would compare reaction quotient to KEQ, then this is basically the same thing, what we're doing down here. And then formation or stability constant is Kf, the equilibrium constant for complex formation, usually much greater than KSP. And then common ion effect is important to know as well. It decreases solubility. So one thing you should know is that common ion effect is the opposite to complex ions. Common ion effect is opposite to complex ions. So it decreases solubility of a compound because complex ions increase solubility. So it's over here. Increase solubility. And then chelation can be used in chelation therapy to kind of take out toxic metals. When a central cation, is bonded to the same ligand in multiple places. So you get this claw effect actually of a it looks like a claw. But search up chelation and you'll see what it is. Okay, now, and this is also related up here about complex ions. Okay, colligative properties are just physical properties of the solution. So physical properties of solutions that depend on the concentration of dissolved particles, but not on chemical identity. It has nothing to do with chemical identity. So Raoult's law is about vapor pressure depression. So you should know this. Boiling point elevation. You should know how to solve for this and do the practice questions again. Freezing point depression, you'll notice is the same formula, basically. Just notice that. It'll help you memorize stuff too. Osmolarity is the number of individual particles in solution. So NaCl dissociates completely in water. So 1 mole NaCl is 2 osmol per liter. Osmotic pressure is the sucking pressure generated by solutions in which water is drawn into solution. So then you need to know how to calculate for that. So these I want to highlight is mostly about doing your calculations and doing your practice problems for them. So because we went through a lot of stuff in this chapter where you have to practice stuff, I'm going to give free practice problems right now and generate some. So let's go and do that. Solutions. Okay, I'm generating some. Okay, everyone, so these are the three practice problems. So right now we have one on molality and concentration units. So a student prepares a solution by completely dissolving 0.5 mole of sodium chloride, NaCl, in 500 grams of pure water, 25 degrees Celsius. What is the molality of the solution? So to solve for molality, I'm gonna put this as a screenshot, use the tool as I designed it to be used. Put it here. And now we're going to solve for molality. So without trying to look at this solution, we're going to go to the review sheet. So we're going to look for molality. Where did it go? Okay. All right, so here's molality. Molality is mole solute over the kilograms of solvent. So let's go back to the practice problem. We'll do it on here. So you have mole solute over kilograms of a solvent. So what did they give us? They gave us 0.5 mole of sodium chloride, so that's automatically 0.5, in 500 grams of pure water. So that's 500 grams of the solvent, right? So that should be here. But the thing is that it's in grams. So we have to convert grams to kilograms. So if I have 500 grams here and I convert it to my kilograms, I should get 0.5. So I get 0.5 kilograms, right? So now what we do is we divide it, and the answer is 1, by the way. So if the answer is 1, then we can go back to our practice question, strike out this one, that one wasn't right, this one wasn't right, this was right. So we checked the answer, and it was correct. Yay. So then we move on to the next question. This one is about molar solubility. So let's go back about molar solubility. Solubility product constant is given to us, so KSP. So let's do the practice question here on the board thing, the paint tool, whatever, because math is easier to draw. First, to find molar solubility, so this is still the molality, whoops, sorry. So to find molar solubility, S, right, we need to use a KSP expression. So we know KSP is equal to, as our review sheet says, where's KSP? Over here, A, B. Man, if I had all the time in the world, I would make a more thorough review sheet. So B is equal to, so they gave us the KSP, 3.2 times 10 to negative 11, and then now we should have some numbers for this as well. So what you want to do first is actually write out the dissociation kind of reaction that would occur. So CaF2, that's your first step, would dissociate into Ca plus 2F. Now, you should know that Ca would be probably positive and fluorine would be negative, and that to have this balance, this would have to be 2 to be neutral, these two. So letting S represent for molar solubility of CaF2, so at equilibrium. So I'm not going to use S, I'm going to use X because that's the way I learned it, so we're going to use X instead of S, but you could use it any way you want. So when you have one of these, you will have one of these. When you have one of these, 2 of these will form. So for every 1 calcium you have here, you have 2, right? So for every 1, you have 2. So that means Ca2 plus, let's say, is equal to X. We don't know its concentration. And then for every 1, we have 2 of these guys. So that'll be 2X, 2F in other words. Okay, so the solubility product expression is, so now we can write out the expression finally, right, is this. So we're going to write it again, but with just the, sorry, I'm trying to do multiple things at once, with just the elements there, or atoms there. And so you have X, and you plug in now 2X. And then we know KSP was 3.2 given to us, so we put 3.2 times 10 negative 11. That was given to us. And then what you need to do is, you need to kind of simplify it. So this X times 2X is 2X squared is equal to 3.2 times 10 to negative 11, right? And then we already did this part. I'm ahead of the game right now. This is good. And now we're going to solve for X. Okay, so you notice the only variable left to solve for is X. So 2X squared, we're going to divide this by 2. is equal to 3.2 times 10 to the negative 11 divided by 2 as well. And then you're gonna, after you divide that by 2, you get x squared equals, what's 3.2 divided by 2? You get 1.6 times 10. And then, did I even do that right? And then you square root. I think we did something wrong here. Wait 1 second. 2. Oh yeah, we forgot to add a square root here. My bad. So this is actually 4x squared. Sorry, I'm ahead of the game, but I'm not really. 4x cubed there. And then you get 4x cubed over here. See, that's why doing your practice is really important. Whoops. I don't know why I'm messing this up right now. It's probably too late at night. That's why. 4x cubed. So KSP is equal to 4x cubed, where S is your molar solubility, but I just did use X instead. So you kind of just solve for X. So 4x cubed is equal to 3.2 times 10 to negative 11, as we did here. We would divide it by 4, right? 3.2 divided by 4 should give you 0.8 times 10 to negative 11. And the answer shows you 8 times 10 to negative 12. But the reason why is because it converted it to scientific notation. That's basically what it did there. So 0.8, to convert it to scientific notation, you move this up. So then it becomes 8, you move the decimal up, and that actually changes the exponent, right? So my advice, if you don't understand how this is working, search up scientific notation for the MCAT or something like that. There's probably lots of people that have done videos on that as well if you're still confused. And then taking the cube root yields 2. So yeah. So the correct answer should be this one. And then you would strike through and get the correct answer. And then same with the next one. This is about solubility. So let's say I chose that one. Oh no, it's wrong. You can take a screenshot, save it in your notes. And your notes should kind of look like this, right? You should have lots of math, lots of stuff showing. You want to focus when you do these practice questions for these ones on the how. How did I get the answer? Not what is the answer, not what is the definition. You want to focus on the how for these ones. And then go through the rest. So I'll pause a little bit for 4 and 5 so that you could screenshot this right now and do them. And then I'll show also the answer solutions here. And then for this one, I'll also show that. So pause and just screenshot. And these are the answers for that solution there. Okay, so that's how you work through solutions. It's a lot of practice problems for concentration and also for colligative properties and also for solution equilibria. So the one we were just doing is solution equilibria for KSP. Okay, now we're on chapter 10. Chapter 10 is about, whoops, let me just do this one. Chapter 10 is about acids and bases. You can't see it here, unfortunately, but because this stuff is covering it, but it's about acids and bases. So the first thing you want to go over is the definitions, the different definitions of acids and bases. So the first definition is Arrhenius, and the second is Bronsted-Lowry, and then we'll go into Lewis. So an Arrhenius acid is when it produces H plus. An Arrhenius base is when it produces OH minus hydroxide. This is hydrogen. And then Bronsted-Lowry acid donates hydrogen. Bronsted-Lowry base accepts hydrogen. So Bronsted-Lowry by definition is focusing on the proton exchange. Proton. It's focused on the proton. And then Lewis acid is different because it's focused on what? Electron pairs. What's accepting electron pairs is the acid, and the Lewis base is donating the electron pair. An important thing to note is that all of these are not necessarily the same definition for the same thing. An Arrhenius acid is not necessarily going to be a Lewis acid, right? So this is an important note down here. Note all Arrhenius acid bases are Bronsted-Lowrys, right? And all Bronsted-Lowrys are Lewis. However, the converse of these statements is not necessarily true. So basically, not all Bronsted-Lowry acid bases are going to be Arrhenius, and not all Lewis acid bases are going to be Bronsted-Lowry. Okay, now we're on to amphoteric species and also polyprotic acids. So we'll go from amphoteric first. A good example of an amphoteric species is water, a species that can behave as both an acid and a base. I'm not sure why they didn't mention this. I think it's over here, is it? Yeah, they didn't mention this, but water has something called autoionization. So autoionization. I should actually just show you a picture. Autoionization of water. Alright, so where's the picture? This is not a good picture. Why is there no good pictures? Okay, here's one autoionization of water diagram that I found. It wasn't the best one. Oh, this one is good. This one is made by Sketchy, which is awesome. They have apparently a free lesson, so you can go to that too. So you can see here that water can mix with water, and what happens is it auto-ionizes, so it reacts with itself. Water is able to react with itself, and that's auto-ionization of water. Khan Academy also has a video on it, so if you're interested, it's also important to note that water has this. So go ahead and watch that too. Because why? Because water is also an amphoteric species. Okay, so what does it mean to be amphiprotic equals amphoteric species that specifically behave as bonded to lauryl acid or base? Polyprotic acid is an acid with multiple ionizable H plus atom, H atoms, sorry, not H plus. Okay, and now we're gonna go into, I'm just thinking of which section is best to introduce first. Okay, the next section they're doing first is properties. So properties, water dissociation constant is Kw is equal to 10 to negative 14 at about 300 Kelvin. So what it means is that water dissociates at this, right? So Kw is equal, this is an important relationship, that Kw is equal to Ka times Kb. So if you knew Ka and Kw, you could solve for Kb. So in the practice problems, they'll make you solve for one of them, right? And you also have to know how to do pH and pOH. This is where you also, now the math is getting a little bit harder if you don't know your logarithms and log rules, basically, log rules. Because you want to be able to know how to do this. Now they're gonna give you weird log. So there's actually a trick to use over here, which is the p-value approximation, which is basically if somebody gives you minus log, let's say a is 3 times 10 to the negative 2. If someone gave me minus log 3 times 10 to the negative 2, how do you calculate this without a calculator? So you have tricks of the trade, and they gave you one right here. You use this, negative b plus 0.8. So what you do is you plug in negative 2 plus 0.3, and that will give you 2.3, right? So that's how you solve for log without having to do that much log work, right? So this is a good hack to use, okay? Strong acids and bases dissociate completely. Weak acid bases do not completely dissociate. So an example is NaCl. If I have NaCl and it completely dissociates into Na plus Cl minus, then that means it completely dissociated, right? But if I have, and it would be a strong acid, a strong, no, sorry, that's not actually an example of acid and bases. Acid and bases is like if you have H plus OH, and that in it, and it dissociates into these fully. My bad. Don't get confused like I did then. Acid dissociation constant, Ka. So you need to know this, and Kb. So they're very similar formulas for both of them. It's just determining whether it's an acid and base, which is different. pKa plus A plus pKb is equal to pKw is equal to 14. So on the P scale, if you know the pH, I don't know if they wrote it here. Yeah, if you know the pH, it's also 14 over here. If you know the pH, then you will know the pOH, right? If you know the pOH, then you should know the pH because the sum of them both will equal to 14. And you'll get better at all of this when you do enough practice, right? So yeah, the way to learn this is through practice questions, not memory. Conjugate acid base and pairs, strong acids and bases go with weak conjugate, weak acid and bases go with weak conjugate. Okay, neutralization reactions. We already went through that before, but I guess we're gonna go through it again. Neutralization reactions form salts and sometimes H2O. Yeah. So these two you can just memorize, these two. This is not practice problem based. There's actually practice problems for conjugate acid base pairs. Okay, now we're on to titrations and buffers, but before we go into those, we're going to do polyvalence and normality. So you should know since chapter 3 almost what equivalents are, what normality is, and what polyvalent is at this point now. So do practice problems for these as well, determining equivalence, normality, and polyvalent. What is a polyvalent? Can donate something that can donate or accept multiple equivalents, right? Okay, and then for titrations, we have half equivalence point, which is a midpoint. The midpoint is of the buffering region, which half the titrant, or I think this is also known as analyte, right? Analyte. If it's still confusing, just watch a video. Has been protonated or deprotonated. Meaning protonated means it gained an H plus, and deprotonated means it lost an H plus. HA is equal to A minus, and pH is equal to pKa. A buffer is formed. Equivalence point, the point at which equivalent amounts of acid and base have reacted. So this formula is important to know to determine the equivalence point. pH at equivalence point. So you should know this. This is memory based and you want to memorize that. Indicators, you need to memorize those literally. So indicators are weak acid and bases that display different colors in the protonated and deprotonated forms. The indicator pK should be close to the pH of the equivalence point. So the indicator would indicate to you what? the indicator should indicate to you something like pH of the equivalence point. So if you have a litmus test, an acid is red, a base is blue, and a neutral is purple. So you have to know this. If you have a test that's phenolphthalein, you just have to memorize these, right? And so the endpoint is when the indicator reaches its final color. So basically titration is like a test, right? An experimental test, or not a test, but yeah, you can call it a test, where you're looking for the equivalence point. And when the indicator finally reaches full color, then we call it the endpoint. Polyvalent acid basis titration is when you have multiple buffering regions and equivalence points. So polyvalent, multiple, not just one, multiple. So here's a titration curve. There's also a lot of different types of titration curves that you should know, and not just this one. This is just an example when titrating a weak base with a strong acid, but there's different examples to know. So Khan Academy has their article on it. So you can go here, and if you don't understand titration, you can go through this. The pictures even came from them too. The one on Mile Down literally looks like it came from Khan Academy. So it's showing you the different titrations. So where can I show you the right one? Let me go up. What is a titration curve, right? Let's attempt to draw some titration curves now. So as you can see, this is a titration with a strong acid and a strong base, okay? And you have to understand why does it look like that. Titration of a weak acid with a strong base looks like this, and then you have to understand why does it look like that. And then you have titration with a strong acid and a weak base, and then you also have to understand why does it look like that. And then titration of a weak base with a weak acid, and it will look like this, and you have to understand why does it look like that. So yeah. And this is what the test looks like. Maybe it's better in light mode to show these ones. And now we have buffers, last but not least. A buffer is used in our own bodies, by the way. And a buffer, what it'll do is it'll resist changes in the pH. So resist changes. Oh, it's right here. Buffering capacity, ability of buffer to resist changes in pH. Maximum buffering capacity is within 1 pH point of pKa. Interesting, right? A buffer is when a weak acid plus a conjugate salt or a weak base plus a conjugate salt. So you can just memorize that in your head. A Henderson-Hasselbalch equation. This one, do your practice problems on it. Do it. Don't skip out on practice problems because CP, your chemical physical section, is heavy on this and heavy on applying your knowledge. So not only should you just know this, you need to understand it deeply and apply it deeply. Okay, now we have oxidation-reduction reactions. I'll stick to light mode for now for fun, I guess. Definitions is that if you have an oxidation reaction, there's a loss of electron. A reduction reaction is a gain. Another way to memorize it is red ox. Red ox. Or actually, no, that's not the right one. Oil rig, my bad. Oil rig. So oxidation is loss, reduction is gain. So gain electron, loss of an electron for oxidation. So that's a way to just memorize it, oil rig. And then with respect to oxidation, obviously it's gaining oxygen, right? Reduction is losing oxygen. And an oxidizing agent is the one that facilitates the oxidation of another compound. So it started this up. It's the reason why oxidation happened. And reduction agent facilitates the reduction, right? So now this balancing by a half reaction method is important to practice. So this is just giving you the steps. So I just recommend reading this probably maybe once the first time and then go right into practice. And then going through the practice, looking at the solution and how to get the right answer step by step, and then reading this over again the second time, reading over this again the second time once you've done practice, knowing the solution step by step, and then read this over again to help help you regurgitate and understand this information, because this is best learned through practice. So just read it one time. Don't read it like 6 million times trying to understand these steps. Sometimes people write down steps or ways of doing things that don't necessarily transfer to other people, so you need to know how do you get the right solution too. Okay, oxidation rules. This is memory based mostly, so just memorize. Any free element or diatomic species is equal to 0. Monatomic ion, charge of the ion when in compounds, group 1A metals, blah blah, +1, group 2A metals, +2. Remember that what A is an A element. Remember what those were when we were doing periodic table stuff. -1 over here, greater En, H equals +1 unless it's paired with a less En element than -1. So you just have to memorize this oxidation number rules. Okay, for net ionic equations, complete ionic equation accounts for all ions present in a reaction. Split all aqueous compounds into their relevant ions, keep solid salts intact. Net ionic equation is when you ignore spectator ions. So spectator ions are present on both reaction and product sides of the chemical equation. So they are emitted in the net ionic equation. So a net ionic equation, and this is a good example. So ignores those. Complete versus net, So complete is like showing everything, all the ions. Net ionic equations only showing the ones that are basically not spectator ions. Okay, so then you have disproportion, dismutation, in other words, a type of redox reaction. The redox is reduction, oxidation reaction. Reduction, oxidation. I don't know why I'm writing out. It's hard to. Let me just show it. Reduction. Here's a redox. Here we go. Redox reactions. Cool. So you can guess it's kind of like both of them. Forming at least two molecules containing an element with different oxidation states. Redox titration. So we went through what titrations were in the last one. So that's why everything builds on each other, right? So similar in methodology to acid-base titrations, however, these titrations follow transfer of charge. Potentiometric titration is when a form of redox titration in a voltmeter measures the electromotive force of a solution. No indicator is used, and the equivalence point is determined by a sharp change in voltage. So basically, you should know the difference between redox titrations and this one. You should know what they are, right? So you should memorize that. Okay, last but not least is electrochemistry, and this is chapter 12. So in chapter 12, electrochemistry, you have different types of cells. You have galvanic cell, and then you have this electrolytic cell. So electrochemical cells, give me 1 second, actually. So I'm just going to go over electrochemistry a little bit more for people that don't really know electrochemistry. So electrochemistry is simply about controlling the flow of electrons during chemical reactions. So in a normal beaker, when something wants to give away electrons, remember we learned about oxidation earlier, and when something wants to take them, they collide directly and release energy as random unusable heat. Okay. So basically, a redox. The genius of an electrochemical cell. So in the cells that we saw earlier, these ones, is that we physically separate the oxidation half reaction from the reduction half reaction. So you're basically making the redox separate, right? So you're separating them into oxidation and reduction and connect them with a wire. To transfer electrons, the atoms are forced to send them across that wire, giving us usable electrical current. So now the electrical current can be usable. So before it would be unusable, but the point is that these electrochemical cells create them as usable. So an intuitive analogy is that imagine water is flowing freely down a cliff into a pool, right? So let's say it's a waterfall that's going into somebody's pool. It creates lots of splashing around, and that's wasted energy. But if you channel that falling water through a pipe, specific pipe, and that pipe moves a water wheel, so if you ever seen a water wheel like that, and the water's flowing, and it moves that water wheel to spin that way, you're now using the water in a way that spins a generator and does work. In electrochemistry, electrons are the water is the pipe, and the circuit device is the water wheel. So the 5 universal laws is true for all cells. All cells. All cells. It doesn't matter what type. And ox. So oxidation is an anode. The anode is the electrode where electrons are lost. Oxidation. Red cat. Okay, so by the way, an ox and red cat are just mnemonics for you to help you memorize, but you don't have to use that mnemonic. Cathode equals reduction. Cathode is the electrode where electrons are gained. Reduction. Electron flow is alphabetical, so electrons always travel externally from anode to cathode. This is the ways to help you memorize, okay? Current flow, I, is opposite. By convention, positive electrical current flows from cathode to anode. Ion migration, this is also important. Like attracts like. So anions migrate towards the anode. Cations migrate towards the cathode. So anions like to go to their anode, and cations like to go to the cathode. At the anode is a site of oxidation, the loss of electrons. Electrons leave the metal strip and enter the external circuit. Metal atoms dissolve into the solutions as cations. So positive. Anode loses mass over time, corrodes/dissolves. At a cathode is the site of reduction where there's a gain of electrons. Electrons arrive from the wire to reduce solution ions. Solution cations grab electrons and plate out. Cathode gains mass over time. So you can just think of them as polar opposites. That will help you to memorize as well. So another thing is the salt bridge. Why is it essential? So the salt bridge is over here, seen over here in a galvanic cell, not in an electrolytic cell. So the salt bridge, without a salt bridge, a galvanic cell dies in a fraction of a second. So you need a salt bridge in this galvanic cell. Here's why. So by the way, the copper in here is the cathode and the zinc in here is the anode. Okay, and here in the electrolytic cell, you have the cathode and anode. So we just went over cathode and anode. All right, so we went over this, went over red cat, electron flow, and current flow. Now we're gonna go a little bit deeper into the salt bridge. So at the anode, new positive ions, Cn2 plus, constantly dissolve into solution, making the beaker increasingly positive, and that's at the anode. Okay, at the cathode, you have positive ions, positive, leave the solution onto the electrode, leaving unpartnered negative sulfates, making the beaker negative. Electrons will refuse to leave a positive beaker or enter a negative beaker. Current immediately stops due to electrostatic break force. So the salt bridge solution is that filled with inert electrolyte. You should know what electrolytes are as well. Anions flow to the anode to neutralize the excess positive charge, while cations flow to the cathode to replace the consumed. So it's basically, the cell bridge is very important because it allows for this transportation or this movement. Well, I'm just going to call it movement, actually. So it allows for that movement over here to here. And this is an important movement. Whoops. So cell diagrams. Cell notation describes an entire cell without needing a diagram. So this is a cell notation. It always reads left to right, anode to cathode. So this is the notation that you use. I don't know if it's on the review over here. It's not even on here. So galvanic and electrolytic. Galvanic spontaneous and electrolytic non-spontaneous. And the thermodynamics is as follows. So delta G is less than 0, spontaneous, right? So we learned that before. And the E cell is greater than 0. So the energy here. Here it is over here, E. Okay, what else do we have? It's showing you over here. So we went over that. What else? Electron flow is chemical energy to electrical energy. It will generate power, but the electrolytic cell requires battery or a power source. So this one requires a battery, and as you can see here, this is the battery up here. So this electrolytic cell requires that battery. All right, the concentration one is over here, by the way, so we could go over it. So delta G is less than until equilibrium, and E equals 0 volt. Okay. Negative, half the cell with lower ion concentration, positive, half the cell with higher ion concentration. And this is key examples in terms of biology. Okay, Daniel cell is on there too, by the way, for galvanic. So we'll follow this through now. So EMF and thermodynamics, electromotive force, that's what EMF stands for, and change in free energy always have opposite signs, so they're always opposite to each other. That's what you have to know here. And these are all the equations you need to be able to practice. So practice those, get practice questions for them. And you also have to memorize Faraday constant, and you also have to know 1 C is equal to joules over V. Okay, and then we have concentration cells, which are specialized form of the galvanic cell. So this concentration is specialized form of this galvanic. So my bad about saying galvanic cell is a concentration gradient between two solutions that causes movement of charge. So rechargeable batteries can experience charging electrolytic and discharging galvanic states. Lead acid discharging lead anode, lead oxygen right there, cathode in concentrated sulfuric acid solution, low energy density. So you have to just memorize that. NiCd discharging CD anode, a cathode here in a concentrated KOH solution, higher energy density than lead acid batteries. And this one you have to memorize. Then more common, NiMH is more common than NiCd because they have higher energy density. So you kind of have to learn these together. Yeah. So cell potentials and Nernst equation. So we'll go through cell potentials first. So reduction potential is where it basically quantifies the tendency for species to gain electrons and to be reduced. So if you're more positive in reduction potential, then you have a greater tendency to be reduced, right? So reduction potential, you have greater potential to be reduced. I guess you could reword it. Standard reduction potential uses that little circle sign. So whenever you see that little circle sign in chem, it means standard, right? So standard reduction potential calculated by comparison to the standard hydrogen electrode, SHE, standard electromotive force, standard E cell, the difference in standard reduction potential between two half cells. So here you go. Here's galvanic plus E, electrolytic minus E. And then Nernst equation. So it'll help you understand this even better by doing practice questions. So this is not just memory based, by the way. Nernst equation is the relationship between concentration, species, and solution under non-standard conditions. Non-standard conditions. So we were just talking about standard stuff. Now we're talking about non-standard stuff. So E cell now is equal to, you need to know the standard minus this equation here. And this is another equation that could be used as well. It's basically, whoops, how do I put this? It's basically, you should memorize this one is probably faster on the test because it's basically R times T is already done for you, and they put it at 0.059, which is basically 0.06 over N, right? And they have F there. But anyway, you can remember both equations if ever need, right? And then here is what you have to memorize when you do nurse equation practice problems as well. So when KEQ is greater than 1, then you have a positive E cell. If KEQ is less than 1, then you have a negative E cell. If a KEQ is equal, then E cell is equal to 0. So that's basically it for all of chemistry. We went over literally everything. So I hope this really helped a lot. So we're going to go try to get some electrochemistry questions going to see how that goes. So we're going to do foundational discrete questions, and we're just going to do 5 for now. Alright, so here are the practice problems I generated. So in electrochemical cells, oxidation-reduction reactions occur at specific electrodes. Which of the following statements correctly describes the operational characteristics of a galvanic voltaic cell? So you have to know what would happen, right? So here we go. B is the correct one, and this is the reason why. And you have to remember red cat, right? So anode is oxidation, and reduction is at the cathode. And then you even have these practice questions here to do the standard potential of the cell, which we just looked at, right? So you would solve for it. Let's say we got it wrong. Then you have to figure it out. Why did I get it wrong? And you have this awesome explanation here. So I'm just going to not talk and just give the questions out so you could just solve them right now. Take your time. We'll give the solutions for free as well. So here's the solution. It was actually A. Here's the work through step by step. Pause the video. Here's another one on Faraday's law, right? So here's how you do it. So I'll just scroll, you can pause here and pause here, screenshot, do your thing, 3 questions. Next one, consider the Daniel cell, right? So that was another, was it galvanic one, galvanic type of cell. And let's say we chose B again, got it right. So here's the solution and the answer, and also the key takeaway, right? Awesome. So then you're going to end your block, and that was the end of your block. Awesome. Okay, so that was the end of the entire review and practice. I hope it was really helpful.